Alright, so we should be live. We should be. Now let's double check if we actually are. Da, da, da. Go live. Manage. Yeah, it seems like we're alive. How much is the delay? Alright, just 1 minute. That's good. 1 minute, I mean 1 second. Alright, amazing. Let me set up some things quickly. Right. And we'll move that over here. Alright, amazing. Okay, so I'm going to be very simple about this. As you guys know, I'm a programmer. And by the way, I have my OBS over here right now on this screen of my third screen to see if everything is going alright. So let's double check a few things. That I can manage chat, etc. Having to log in, obviously. And there we go. We should be live. Yeah, alright. So, a small introduction on what I'm about to do and what I thought was perhaps interesting for you guys. So, as you guys know, I'm a programmer. I've been programming since I was 7 years old, which is right now already 2 decades, 20 years of programming. I've finished university in computer science, where I majored in AI, design patterns, and complex mathematics. I got the enthusiasm, I gained enthusiasm in neural networks around 2016 when the first interesting papers came out. And a lot of my university work actually, and my scriptures were built around neural networks and how they work and how you can build them, etc. Right now it has been a little while since I have, well, worked with them, and I thought it was a good time to refresh everything. So right now it's very simple actually. I am following what is called the playlist Neural Networks 0 to Hero from Andrei Karpathy. Andre, if you are going to watch this live stream or video, sorry if I butchered your name. And I was already working through this. I did the first video of it, of how to create a neuron and how to start with micrograd, and actually how backpropagation and forward passes work. And last night I had the idea, very simple actually, that, well, why let's not just live stream it while I learn. Nothing bad can happen from that. I'm not showing any intellectual property from myself in regards to coding algorithms, just here learning, and if somebody wants to join, well, amazing, and then they can learn with me or refresh with me. Andre, I have, as you can see, the video in the bottom corner of you with your playlist. I have put the full work and links to watch your video tutorial in the description as well, so definitely check it out. Andre is amazing in regards to explaining anything from scratch. So if you are into computer science and you would like to learn how neural networks work, definitely give him a follow and a subscribe and go over it. Um, I already did a little bit of work in regards to this video over here, which is actually the first part. It's the spelled out intro to language modeling, building makemore. Basically what it is, what we're going to do is we are going to step by step with Andre recreate makemore, which is like a name generation neural network. And yeah, from there on out, it's very simple. I'm just following what he's doing and refreshing myself on how PyTorch works, how current large language models works, and eventually, once all of this is done, I will transition everything that I've learned into my own algorithms as well. So I already have several algorithms that work with machine learning and deep learning in regards to price prediction or strategies that I've trained myself and let a neural network learn those strategies. But I want to refresh everything basically, and yeah, right now I will just be sharing basically the journey with you guys because I thought, well, why the hell not? And that's basically the works. So let's continue, I would say. And if there are any questions anywhere along the line, feel free to ask them. I'm open for everything. So in the meantime, I will just continue where I left off, which was basically that we were reading in a text file from makemore, and that we were splitting everything up into the most combinations that occur with the first and second character in names. And why do we need this? Because eventually when we're going to make a predictive engine, what large language models do and what just language models do is that they predict the next set of characters or character. And this is basically what we are right now doing. We are preparing data, and right now what we did, instead of having it in a dictionary, we converted it to an array. Because eventually, when we are looking at time and space complexity, dictionaries can have a little bit of overhead, and arrays just progress those things more rapid. From my understanding of, well, general programming. So that's basically where I left off, and let's continue.
So this is the 28 by 28 array, and this is structure. But even this, I would say, is still pretty ugly. So we're going to try to create a much nicer visualization of it, and
I agree.
that. The first thing we're going to need is we're going to need to invert this array here, this dictionary. So S to I is a mapping from S to I, and in I to S, we're going to reverse this dictionary. So iterate over all the items and just reverse that array. So I to S maps inversely from 0 to A, 1 to B, etc.
Makes sense.
So we'll need that. And then here's the code that I came up with to try to make this a little bit nicer.
Okay, so let's read through it. Basically what he does, he creates a plot figure of 16 by 16. Then he shows the CMap, and then with a two-dimension, he loops over the two-dimensional array of characters and the occurrences. And what he does is that he puts the character string of the two characters with the text, and then he turns the axis off. I mean, I guess that should give indeed a better way of showing it. So let's just copy his code for a second. So do not expect me to actually program a lot of things. Of course, during everything that I'm doing here, I'm basically just following a tutorial, right? And why I'm doing that mainly has to do, hold on a second. So basically what I'm doing is trying to follow what he's doing as much as I can in regards to knowing how to think like he does, um, because it is his tutorial nonetheless. It is very important though that it is good to understand like why he is doing what he is doing. And if I would see something where I'm like, alright, I would do that differently, then I would definitely do so. One thing that I don't like as much with machine learning and AI in general, a lot of it is done on Python, in Python, and I can understand why. The thing that I dislike is that I mainly program in C#. So I have like worked around with Skylearning, etc. a lot, and they have like a library for PyTorch to C# as well. I think it's called PySharp, if I'm correct, or something like that. Um, but yeah, it's always getting used again to like the syntax of a particular language to figure out how everything works again, which is fine, you know. But so also to take into consideration is that this tutorial itself is already quite old, and I noticed that with the previous video that some syntax has been deprecated. For example, in the previous tutorial there was where he called the required gradient and he set it to true, like the naming completely changed in the current PyTorch library. So I wouldn't be surprised if, for example, here in matplotlib or something like that, something is different as well. And you might be wondering, why do I not just go into his code base and copy paste this over? It's literally due to the fact I want to go over this for reasons like that, like just stupid syntax things that I have to learn again, which is fine, you know, but name n is not defined, so nmap is n not defined, though. N is not defined. Wait, n is defined. Hold on. I have to run everything again, probably. And then words not defined, yeah, obviously. Okay, hold on. Restart kernel, run from start. Now everything runs. Nice.
We create a figure, we plot n, and then we visualize a bunch of things here. Let me just run it so you get a sense of what this is. Okay.
Yeah. Hey, what's this? Name idols is not defined. Is idols not defined? I am pretty sure that we indeed did not define. No, we did not define idols. Hold on. So what we forgot to do is define what he was saying, like the array of all the items, basically. So if we run making syntax errors every time. And now it should run, but now we are getting something else. Alright, center, blah, 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 blah. And we made a typo here again. Alright, there we go. So basically what we have right now done, we will continue in the tutorial obviously, but we have to think about what we have done. So what we did, for every word, we figured out our pairing and we count how many times that pairing happens. So we do that here. So we have our sorted list from words, and what we do is that we pair them up, and here with that pairing, basically what we do, we make a counter, we put those in a list, and here with the ITOS, what we do is that we put them in a single array, I think it is. What's the dictionary actually? Yeah. And then basically what we did with this code, if I'm correct, we did indeed the pairing and then the counting alphabetically, right? Yeah.
So you see here that we have the array spaced out, and every one of these is basically like B follows G 0 times, B follows H 41 times, so A follows J 175 times. And so what you can see that I'm doing here is, first I show that entire array, and then I iterate over all the individual little cells here,
Yeah.
and I create a character string here, which is the inverse mapping I to S of the integer I and the integer J. So those are the bigrams in a character representation.
Mm-hmm.
And then I plot just the bigram text, and then I plot the number of times that this bigram occurs. Now, the reason that there's a dot item here is because when you index into these arrays, these are torch tensors, you see that we still get a tensor back. So the type of this thing, you'd think it would be just an integer, 149, but it's actually a torch.tensor. And so if you do dot item, then it will pop out that individual integer. So it'll just be 149. So that's what's happening there. And these are just some options to make it look nice. So what is the structure of this array? We have all these counts, and we see that some of them occur often, and some of them do not occur often. Now, if you scrutinize this carefully, you will notice that we're not actually being very clever. That's because when you come over here, you'll notice that, for example, we have an entire row of completely zeros. And that's because the end character is never possibly going to be the first character of a bigram, because we're always placing these end tokens all at the end of a bigram.
Makes sense.
Similarly, we have an entire column of zeros here, because the S character will never possibly be the second element of a bigram, because we always start with S and we end with E, and we only have the words in between. So we have an entire column of zeros, an entire row of zeros, and in this little 2x2 matrix here as well, the only one that can possibly happen is if S directly follows E. That can be non-zero if we have a word that has no letters. So in that case, there's no letters in the word, it's an empty word, and we just have S follows E. But the other ones are just not possible. And so we're basically wasting space. Not only that, but the S and the E are getting very crowded here. I was using these brackets because there's convention in natural language processing to use these kinds of brackets to denote special tokens, but we're going to use something else. So let's fix all of this and make it prettier. We're not actually going to have two special tokens, we're only going to have one special token. So we're going to have
one special token, and then I would assume he is going to eliminate the E, I think.
n by n array of 27 by 27 instead. Instead of having two, we'll
Yeah,
just have one, and I will call it a dot.
exactly. So why I thought he was going to do that, it makes life just easier. That's with what he explained.
Okay. Let me swing this over here. Now, one more thing that I would like to do is I would actually like to make this. Okay. me swing this.
Okay, he wants to put the IDOS over there, which is fine, I guess. We can do that too. We'll just remove that one. And then we have our forwards. Import, yeah.
Over here. Now, one more thing that I would like to do is I would actually like to make this special character have position 0. And I would like to offset all the other letters off. I find that a little bit more pleasing.
Fair enough.
So we need a +1 here so that the first character, which is...
Yes, so that we indeed will never have that. Fair.
will start at 1. So S to I will now be A starts at 1 and dot is 0. And I to S, of course, we're not changing this because I to S just creates a reverse mapping and this will work fine. So 1 is A, 2 is B, 0 is dot.
Okay, let's just double check this. So Stowy is this, and ITOS is that. Yeah.
So we reverse that. Here we have a dot and a dot. This should work. Fine. Make sure I start at zeros. Count. And then here we don't go up to 28, we go up to 27. And this should just
Makes sense.
work. Okay. So we see that dot dot never happened. It's at 0 because we don't have empty words.
Smart guy. Alright. Maybe I should put the correct index. Now we have the correct index. There we go. So dot. No. Alright.
Then this row here now is just very simply the counts for all the first letters. So J starts a word, H starts a word, I starts a word, etc. And then these are all the ending characters. And in between we have the structure of what characters follow each other. So this is the counts array of our entire dataset. So this array actually has all of the information necessary for us to actually sample from this Bigram character level language model. And roughly speaking, what we're going to do is we're just going to start following these probabilities and these counts, and we're going to start sampling from the model. So in the beginning, of course, we start with the dot, the start token dot. So to sample the first character of a name, we're looking at this row here. So we see that we have the counts, and those counts are telling us how often any...
Yeah, so this is very interesting. So basically what we have done with the data set that we have already, and he's probably going to explain this. So the way that it's programmed right now is that when to indicate the start and an end of a name, we have a dot in front and a dot in the end. So this Y column over here basically gives you like, alright, in general, a name in the data set that we have of 32,000 names. Of those 32,000 names, 6,763 end with N. And what we see here is that 4,410 start with A. So that's quite interesting. Everything what's in between here is basically what's within the name. So it doesn't really mean that these are the the first two characters. It can be the first two characters, but can also be the second and the third and the fourth and the fifth, etc. So what we see in this data set is that 4,410 names start with A, and 6,640 and end with A, and 6,763 names end with N, which is quite interesting actually. So what we potentially could assume if we create a neural network from this would be that a lot of the new names that are being created will potentially start with an A and end with an A or end with an N. That's what we potentially would assume. And if we're going from statistics, so we have a data set of 32,000. That basically means that 1 in 5 names will start with an A, will end with an A, or start with an N. So let's say if we have a trained neural network, in regards to probabilities, what we could say with the trained data set that we have is that for every 5 names generated, we will at least see one name that end with an A, that end with an N, and maybe one name that starts with an A, which is which is interesting.
One of these characters is to start a word. So if we take this n and we grab the first row, we can do that by using just indexing at 0, and then using this notation colon for the rest of that row. So n0 colon is indexing into the 0th row, and then it's grabbing all the columns. And so this will give us a one-dimensional array of the first row. So 0, 4, 4, 10, 0, 4, 4, 10, 1, 3, 0, 6, 1, 5, 4, 2, etc. It's just the first row. The shape of this is 27. It's just the row of 27. And the other way that you can do this also is you don't need to actually do this. You just grab the 0th row like this. This is equivalent. Now, these are the counts. And now what we'd like to do is we'd like to basically sample from this. Since these are the raw counts, we actually have to convert this to probabilities.
Okay, so I just went over that.
And we'll have to convert this to float first.
That's hilarious.
Are converted to floating point numbers. And the reason we're creating floats is because we're about to normalize these counts. So to get the probability distribution here, we want to divide
by the sum.
P divide P dot sum.
Yeah. Oh, that's hilarious. Yeah, so basically what he says that we do over here is, so we have this tensor. The nice thing with tensors is that since a tensor is like a matrix basically, in this case it's a matrix of a single row matrix. But with matrices, you can, in the code behind probably of PyTorch, so if you would do it manually, you can divide, subtract, the dot products, all those kinds of things you can do with matrices. So basically what we just do, when we do P divided by the sum of everything within P, basically what it does, it will, with P.sum, it will just count everything up, and then what it does here, P divided by that sum, it will divide each individual tensor value by that sum. And then indeed what we have is the normalized value and probability. So let me get that example of A, for example. So A was that for 4400. What we see is apparently that there is around a 13.77% chance that a name will start with A. So if we would say P start, right? Because P is the start character. This is P start. And what I expect if we would like if we would do bn, so bn, and if I am correct, it would be like this. So we take the 0 column and then all the rows. I assume that would work. Just double checking. Yeah, b and 60. Yeah, okay, that works. Amazing. Okay, so if we then do b and divided or b starred, that's sum. So what I said was that 1 of 5 names would end with an A, right? So that would be about a probability. So the probability will probably be a little bit larger than 1 of 5. But let's say it's 1 of 5, right? Then we expect that the probability will be 0.20. In this estimation, it will probably be like 0.23 or something like that. I might be off by that, but oh yeah, so 0.2073. So there's a 20.73% chance that a name will end with A.
And now we get a vector of smaller numbers, and these are now probabilities. So of course, because we divided by the sum.
Yeah, and the thing with probabilities is, so basically what we just did here is that these probabilities are percentages. So if you would do them times 100, you will get the percentage chance that something is, what the probability is for a character to be there.
The sum of p
You'll probably get into this.
1. So this is a nice proper probability distribution. It sums to 1, and this is giving us the probability for any single character to be the.
That's also pretty good what he explains here. So with probabilities, if we have a set of different outcomes, and we know the probability of everything, then when you do your calculations, the probabilities of every set item, if you sum them up again, it should indeed result in, again, 1. Because what is 1? 1 is 100%. And what is a probability? A probability is just a chance in percentage-wise that something occurs, right?
First character of a word. So now we can try to sample from this distribution. To sample from these distributions, we're going to use Torch multinomial, which I've pulled up here.
Okay.
So Torch multinomial returns out samples from the multinomial probability distribution, which is a complicated way of saying you give me probabilities and I will give you integers.
Fair enough.
So this is the signature of the method, and to make everything deterministic.
So torch the multinomial, the input, so that's probably like the tensor, right? B star. Number of samples will be like the sum. Replacement false. What does replacement false do? Replacement bool optional, whether to draw with replacement, okay.
We're going to use a generator object in PyTorch. So this makes everything deterministic. So when you run this on your computer, you're going to get the exact same results that I'm getting here on my computer.
We'll see if that happens. I'm known to screw things up, so especially with syntax errors.
Here's the deterministic way of creating a torch generator object, seeding it with some number that we can agree on. So that seeds a.
Okay, basically for everyone that doesn't know what a seed is, once you're working with random generators, random generators are, in computer science we don't have total random. Basically what random is, and what happens a lot on the background, when you call random, basically what your computer does most of the time, it will get the clock frequency of your CPU at that time, which can be a number, and then it does some calculations and applies that to a range of values. That's basically what random is most of the time. But when you use a manual seed, you basically set that Hertz frequency of that, how random is generated, always to the same number. Which basically what he says here, like with an agreed number, which means that if I would do the same thing that he places here, I should get the same result due to the fact that we use the same seed, which is 214, 7483, 647, right? Torch.random free generator equals G. So basically what I think that this does is that due to the fact, so the generator G that we have here, basically what we do is that we pass that to torch.rand. Normally what random does, what I just explained, is it uses, for example, the clock count of the CPU, of the crystal that's in there. But due to the fact that we now use a manual seed, that will probably be overridden, and that then results in us gaining the same random number. At least it should. It should. One good thing to understand though is that he uses B, but he overrides B. Does that matter? No, it doesn't really matter in this case. Okay. So what I was thinking about is due to the fact that he used B earlier in his statement, I use B start and B end, and he just uses B, right? But then he then overrides B in this next segment, so what he did here doesn't really matter anymore.
Generator gives us an object G, and then we can pass that G to a function that creates here random numbers. Torch.rand creates random numbers, 3 of them, and it's using this generator object as a source of randomness. Without normalizing it, I can just print. This is sort of like numbers between 0 and 1 that are random according to...
Let's quickly just do what he did. Yeah, so here's what I told you, right? Because we use the same seed, you guys can probably not see it, but his numbers in the tensor are 0.0081, 0.3542, 0.1054. I'm getting the exact same numbers, and that has to do with like the generator seed that we copied over from them. So that's how we know that we are getting the same output as him in the tutorial. If, for example, I would not use the generator here, then you will see that I will get different numbers all the time, every time, because it's not using the same seed. It will probably, like, every time when I press enter to reload it, it will use, this is what most of the times happens, again, the Hertz crystal count of the CPU or something like that. So, due to the fact that we use generator G, what happens is then that we, hello, yeah, I forgot a comma. Yeah, I forgot a comma. Thank you, compiler. Due to the fact that we use a manual seed, we do not make use of that randomized crystal count. And that's why we get the same tensor all the time.
Thing. And whenever I run it again, I'm always going to get the same result because I keep using the same generator object, which I'm seeding here.
Exactly.
If I divide, to normalize, I'm going to get a nice probability distribution of just 3 elements.
Yeah.
And then we can use torch multinomial to draw samples from it. So this is what that looks like.
Okay, let me quickly write this over because I want to know what he's doing here. So we have that torch dot multinomial where we put in P, so the tensor that we just created, number of samples is 20. Samples, no samples. Replacement equals true. Generator equals G. Okay.
Torch multinomial will take the PyTorch tensor,
Yeah.
multi-distributions. Then we can ask for a number of samples, let's say 20. Replacement equals true means that when we draw an element, we can draw it, and then we can put it back into the list of eligible indices to draw again. And we have to specify replacement as true because by default, for some reason, it's false. And I think, it's just something to be careful with.
Why would you put it on false by default? Like, I know that I'm a bit rusty on my neural networks, right, in deep learning, but I'm trying to think about why would you, in a normal distribution, why would you want to remove a certain number, because then you will get distinct numbers.
And the generator is passed in here. So we're going to always get deterministic results, the same results.
Yeah.
So if I run these two.
So double check 112.0.0.2 11.0.0.0 11.0.0 11.0.0.1. Yeah, same.
We're going to get a bunch of samples from this distribution. Now, you'll notice here that the probability for the first element in this tensor is 60%. So in these 20 samples, we'd expect 60% of them to be 0. We'd expect 30% of them to be 1. And because the element index...
So literally at the part where he now gets is this is basically what I just explained, right? So what I said about the probabilities, it's actually a percentage wise, but it is you have to do it times 100 to get the percentage for us to understand. So if I am correct, I just want to test one thing here. So if I would use B start, right? So B start. Was it B start? Yeah, B start. And I would sample. Let's say I would sample 30. 30? Is 30 a good one? Okay, now let's do 10. So if I would sample this, if I'm correct, what I would expect is that around 4 in the tensor, I would expect 4 A's. Based on generate G. Is that correct? A is 1. Let's run that again. I would expect that index 1 would occur a little bit more often, actually. That's interesting. Because the probability of... Oh, wait. So 10... 20% of 10. Okay, so I would expect it to come twice, basically, every time. Yeah, okay. So that does work. To a degree, at least. Again, it's probability, so it's not a given, it's probability, so there's a chance in it happening.
Has only 10% probability. Very few of these samples should be 2. And indeed, we only have a small number of 2s. And we can...
What are your education qualifications? From Stefan Somaya? I'm sorry if I butchered your name, mate. So basically, for your idea, I've been programming since I was 7. I'm 27 right now, so I've been programming for around 2 decades right now. And I finished my computer science degree at the University of Windesheim in Zwolle, the Netherlands, where I basically specialized in the deepening semesters of AI, complex mathematics, and design patterns. And basically what that means is that it's not calculus what I've done, but where I shine in is basically writing low latency code that has very little overhead and is very easy testable and reusable. then over the past years, I've done some work as well, obviously. Uh, and we could get into that. But my general education is like just a lot of self-taught stuff because the universities in the Netherlands don't really actually teach neural networks and AI. They do it a little bit, but eh. So that's why I also took that deepening semester. But a lot of it is self-taught and like just keeping up to date, and that's what I'm doing here right now as well. Like the last time that I touched neural networks in this sense to understand how large language models work is a while ago. Like I did my whole end thesis actually on machine vision. It was actually with a multinational company for which I designed an open source machine vision um, algorithm, which basically with 3 cameras could determine an object in 3-dimensional space, the coordinates, and like the distance from a robot. That was my end thesis. And they actually sold that to Amazon. So I got screwed right now, but that's fine. But my education qualifications is pretty bad. But I just the official paper I finished university with a computer science degree.
Sample as many as you would like.
I
And
finished it by the way. Right now it's 2026. I finished it in 2021. But honestly, like the uni part was not that hard, due to the fact that I had been programming for so long and always been focused with high school, etc., in complex mathematics already, like algebra. It was not like I literally went for uni for the paper, you know, like when I studied. So that was around 2017 to 2021. Nowadays it's a little bit different. To get a job, you basically like you had to in the Netherlands you had to finish school. So if you didn't have your paper that you finished something, you would not be hired. So that's basically why I did it at that particular time.
the more we sample, the more these numbers should roughly have the distribution here.
Yeah. So what he's talking about here right now is basically the law of large numbers. So what I did before is that I did 10 samples of B start, right? And I was like, okay, I didn't see index 1, so A, coming that often to the foreground. The thing with probabilities is and the law of large numbers is when probabilities get more accurate mm, in the larger data set you generate. So let's say that I did my P start, where I said that the probability was 20% for a letter for A, which is index 1. To get there, I would expect on 10 indexes, I would expect at least to see in the tensor 2 times 1 occur. But due to the fact that the sample size is so small of 10, um, the probability of it happening there, again, if you get into advanced in statistical mathematics, it remains a probability. But once, and this is with trading as well, like if you are going to calculate EV, so expected value, 10 trades can basically give you an expected value with a standard deviation. It can put you all the way to the left. But if you know that your EV in general is 20 cents, for example, and you have 1,000 trades, then the probability of getting closer to that 1,000 times 20 cents will be way closer. But it's also possible that, for example, with just 10 trades, that you are actually in the negative. And that's where the law of large numbers comes to. Um, the more, if you know from a large data set that the probability is a certain percentage, then if you do it for a very large amount of times, it will become more true.
So we should have lots of zeros, half as many um, ones, and we should have 3 times as few. Sorry, as few ones, and 3 times as few.
Yeah, so basically what stands here is that with the numbers 0, 1, and 2, he says that the number 2 has like a 9% chance of occurring. So with a sample size of 100, we would expect 2 to be in here around 9 times. And then if you would get with a standard distribution, it can potentially be, with quick calculation, it could be like 7 to 11.
Twos. So you see that we have very few twos, we have some ones, and most of them are 0. So that's what torch-type multinomial is doing. For us here, we are interested in this row. We've created this P here, and now we can sample from it.
Yeah, so that's basically what I did before, right?
Seed, and then we sample from this distribution. Let's just get one sample. Then
so just for now, let's stick with what he's doing as well to ensure that we keep up to date with him. Wait, what did I do? Control C. Everything should be okay. Yeah, it should be okay. Okay, I didn't change anything, did I? Wait, I did. Alright, see sorted list. So let's see if I changed anything else. I'm still getting used to Jupyter Notebook, to be honest. Like I said, like I officially, for the past few years, I've programmed a lot in C#. So I have to get used to Jupyter Notebook and Python syntax again. Yeah, so he wants us to... Yeah, he wants the seed, then he wants to use torch-type multinomial, that we use it on that B start, basically. Yes, B start, number of samples, he wants to sample it 1 times, fine. Replacement equals true, and generate a G. Okay, due to the fact that we created G over here, we can remove it here for now. Like, it has no use declaring it set second time. Tensor free.
see that the sample is, say, 13. So this will be the index.
Here is something interesting though. I used B, he used B as well, right? Yeah, so he used 0, float, B start. We just use the same B samples number 1. This is all the same though. So here's something strange though. We use the same seed, but he's getting tensor 13 and I'm getting 3. So let me quickly rerun all of this to ensure everything is still up to date. I'm still getting 3, so I don't think I made a mistake. There might be something in the background of PyTorch that changed a little bit, but it's fine.
And you see how it's a tensor?
So let's quickly comment this out. So we do get the same probabilities as him, which is correct.
That wraps 13. We again have to use .item to pop out that integer. And now index will be just number 13. And of course, we can map the I to S of IF.
Yeah, so this normally shouldn't have, so I might have made a mistake somewhere along the line. Because with the same things that we used, it should give the same. Double check the seed, 2147 483 647. Yeah, it's the same manual seed. Generator G item. Interesting that he gets 13 and I get 3. That shouldn't happen. Everything was up to date. Alright, let's just continue.
Figure out exactly which character we're sampling here.
So he's sampling M, and I'm sampling C if I'm correct. Why I'm saying C is because, wait, am I? Yeah, I'm sampling C. Because 0 is dot. Yeah, C or B? C, there we go.
Okay. So we're saying that the first character is M in our generation. And just looking at the row here, M was drawn, and we can see that M actually starts a large number of words. M started 2,500 words out of 32,000 words. So almost a bit less than 10% of the words start with M. So this was actually a fairly likely character to draw. So that would be the first character of our word. And now we can continue to sample more characters. Because now we know that M started, M is already sampled. So now to draw the next character, we will come back here and we will look for the row that starts with M. So you see M, and we have a row here. So we see that M dot is 516, MA is this many, MB is this many, etc. So these are the counts for the next row, and that's the next character that we are going to now generate. So I think we are ready to actually just write out.
Okay, so that's basically what. So what he's trying to do right now is based on probability. We are creating a new name, and basically what he is explaining is that due to the fact that we sampled M from the starting letter, that means that if we go to the second row, which is Y, which is like the next combinations in M, what we expect is that, for example here, that if we sample the next character, it will probably be A, because that's the highest probability, right?
Indeed, because I think you're starting to get a sense of how this is going to go. We always begin at index 0, because that's the start token. And then while true, we're going to grab the row corresponding to index that we're currently on. So that's N array at IX, convert it to float.
What's it, NIX? So let's double check. Yeah, NIX is the torch tensor. Yeah, that makes sense. Yeah. NIX.float
is our P. Then we normalize the speed to sum to 1.
So then we do the same stuff. Basically what we do here, and then I expect that he wants to like normalize that all the time. So we already did G there, so we can do. This is what I think he will do. And then IX and IX is torch multinomial. Yeah, makes sense.
I accidentally ran the infinite loop. We normalize P to sum to 1. Then we need this generator object. And we're going to initialize.
Just because you want it, sure, we will initialize it here as well. It wouldn't need to be reinitialized because, again, we already ran this piece of code. Like in production code, you would not reinitialize it again. Like we will probably, due to the fact that these are examples, we will probably in this tutorial remove these later on.
Up here, and we're going to draw a single sample from this distribution. And then this is going to tell us what index is going to be next.
Yeah.
If the index sampled is 0, then that's now the end token. So we will
Fair enough.
Otherwise, we are going to print S2I of IX.
Yeah. Does that make sense? I think you will get the error as well. Oh yeah. So I was correct.
And that's pretty much it. We're just this should work.
Yeah.
Okay, more. So that's the new thing that we've seen.
Oh my god. That's a lot of letters. That's a lot.
With N. The next step was O.
Okay. What's rule Ix if Ix equals 0? Let me quickly print an air. Okay, fair
And
enough.
R. And then dot. And this dot we printed here as well. So let's now do this a few times.
Hello, Ara. I'm not going to try to pronounce the rest of your name, mate.
So let's actually create an
Also, just counter 0, just for now. What I will also do. Plus is 1. I do not want names longer than... let's say longer than 5 characters, right? So right now it should break after 5 characters. Yeah, okay.
out list here. And instead of printing, we're going to append. So out.append this character. And then here, let's just print it at the end. So
Sounds fair enough. IX, and then we print out there, right? Yeah.
let's just join up all the outs. And we're just going to print more. Okay?
What do you mean, Era, with what are the minimum requirements for the quant job? Do you mean like in general requirements to be a quantitative like a quantitative trader or programmer, or? Like the general requirements, what I would say. Like it depends at which firm you want to work, I guess, because a lot of quant firms, some use Rust, some use Python, some use C Sharp, some use Java, but in general, I think that a main requirement, yeah, so okay, so like regular quant trader, like coding language and all. So um, again, it depends at what firm you are trying to work. Like what I mentioned, some firms use Rust, some use C, some use C++, some use Python, some use C Sharp, some use Java. But I think in general, the language doesn't really matter. It's more that you the basic fundamentals of programming for quant trading. One thing that's very important is low latency code, because the earlier you can get to entering a trade, the better your fail position will be eventually. So that's probably priority number one. Learn how to create low latency code, which Dan would say that you need to know how to write code that's very low in time complexity. So you need to know certain design patterns and algorithmic patterns, how to quickly index and move over certain structures. So uh, something that you potentially never want to do is like two for loops, using two for loops to iterate over an array. Like you probably want to make use of jump tables or things like that. And I think that's the number one requirement basically. Like, of course, you have to be a good programmer, but a very good understanding of making low latency code with a very low time complexity that's not heavy on the CPU and a garbage collector. That's one of the most important things, I think.
Now we're always getting the same result because of the generator. So if we want to do this a few times, we can go for I in range 10. We can sample 10 names. We can just do that 10 times.
Sure. Yeah, unexpected column. Uh, does that make sense? This makes sense. Yeah.
And these are the names that we're getting out. Let's do 20.
Yeah, so I probably made a mistake somewhere along the line. Again, I was explaining, like, I'm using the same manual seed, so I do expect that we get the same results right, but for some reason, it was not given the same result. So if I would remove this counter, uh, like I'm getting an infinite loop because we're never like indexing that point, the dot for some reason. I'm not in the mood to get over it. But for now, I would just like keep my counter with names uh, to 10 characters.
I'll be honest with you, this doesn't look right. So I stared at it a few minutes to convince myself that it actually is right. The reason these samples are so terrible is that Bigram language model is actually just like really terrible.
No
Like,
shit.
and you can see that they're kind of like, they name a little bit like Keanu, Riley, etc. But they're just like totally messed up.
Dicky.
And
What a
the
name.
reason that this is so bad, like we're generating age as a name, but you have to think through it from the model's eyes. It doesn't know that this age is the very first age. All it
Yeah.
knows is that age was previously, and now how likely is age the last character? Well, it's somewhat likely, and so it just makes it last character. And it doesn't know that there were other things before it, or there were not other.
Let's quickly rename this to P and just remove this. I doubt it has to do with that, but like the thing is we get the same probabilities here, we get the same probabilities here. Let me quickly remove all those things. This doesn't matter anymore. Doesn't matter anymore. Yeah.
Before. And so that's why I'm generating all these like nonsense names. Another way to do this is to convince yourself that it is actually doing something reasonable, even though it's so terrible, is these little p's here are 27, right? Like 27.
B is the shape of 27. Yeah, that's correct because the alphabet plus 28. Hold on. B shape is 28 and not 27. I did make a boo-boo somewhere, didn't I? Yes, I did. I saw where my issue is. Oh my god. No freaking way that that was it, right? Did I forgot to do that? "28." He has 27, so would it be due to this? It cannot be. That would not be the issue, right? It should not be the issue, at least. Like, this is correct, the display of this. +1. Which should be correct. Okay, so that's the issue. Like our tensor P has 28 things. So dot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have an extra tensor in P. Yes, we have this whole column here. So yeah, that is actually interesting. So then the question becomes how. Oh no, I didn't. Was that the initializing of the initial array? That's probably that probably was the issue. I'm pretty sure we'll get to the B shape of 27 now as well. Yeah, 27 and oh. Okay, at least now we have the same shape again. There might be still a bug somewhere else, but like again, if I remove this counter, we still have an infinite for loop. I cannot be bothered to like figure it out, but yeah, cannot be bothered. I will figure out where I made that syntax error somewhere.
So how about if we did something like this? Instead of P having any structure whatsoever, how about if P was just torch dot ones of 27. By default, this is a float 32, so this is fine. Divide 27. So what I'm doing here is this is the uniform distribution, which will make everything equally likely.
Yeah.
And we can sample from that. So let's see if that does any better. Okay, so it's this is what you have from a model that is completely untrained, where everything is equally likely. So it's
Yeah.
obviously probability. And then if we have a trained model, which is trained on just bigrams, this is what we get. So you can see that it is more name-like. It is actually working. It's just bigram is so terrible.
Yeah, this is where neural networks will come into place.
Efficiency that we have going on here. Because what we're doing here is we're always fetching a row of n from the counts matrix up ahead.
Mm-hmm.
And then we're always doing the same things. We're converting to float and we're dividing. And we're doing this every single iteration of this loop. And we just keep renormalizing these rows over and over again.
So we should pre-cache it.
So what I'd like to do is I'd like to actually prepare a matrix capital P that will just have the probabilities in it. So in other words, it's going to be the same as the capital N matrix here of counts, but every single row will have the row of probabilities that is normalized to 1, indicating the probability distribution for the next character given the character before it. as the
Yeah, that makes sense. I'm just double checking something.
row we're in. So basically what we'd like to do is we'd like to just do it up front here, and then we would like to just use that row here. So here we would like to just do p equals p of ix instead. Okay.
Makes sense, basically what I said all the way at the beginning. So p equals p of ix. He wants to do it above there, which is fine, but yeah, sure, why not?
The other reason I want to do this is not just for efficiency, but also I would like us to practice these n-dimensional tensors, and I'd like us to practice their manipulation, and especially something that's called broadcasting that we'll go into in a second. We're actually going to have to become very good at these tensor manipulations, because if we're going to build out all the way to transformers, we're going to be doing some pretty complicated array operations for efficiency, and we need to really understand that and be very good at it.
So this as well, right? So error. This is something that comes back all the time. I don't know if error is still here, but in any, if you are a programmer and it doesn't, especially in nowadays. So if you're working with data science or something like that, the best thing to understand is how to write low latency code and write code that doesn't recall itself. So one of the things to do is, like, if you can generate a certain item once, just do that and don't redo it all the time. Same with like generating objects. If you can use something like object pooling instead of, and then when you need to generate a new object, instead of creating it with the new keyword in C#, for example, if you can just grab the object from the pool and then set the values to the object, then that is lower CPU overhead than it is with generating a completely new object that has to be allocated to memory, etc. If you use it from the pool, then you can already generate those objects at the start of the program, which will cause a little bit of overhead early on. But later on down the line, in more important situations, what will happen is that it will be more rapid. Because like the changing of something in memory is more rapid than allocating new memory, saving it to the heap, um, and yeah, instead of just manipulating it once on the heap.
So intuitively what we want to do is we first want to grab the floating point copy of n, and
I
we
can
want to
get
draw
that.
a line here, basically. And then we want to divide all the rows so that they sum to 1.
Yeah.
So we'd like to do something like this. P divide p dot sum. But now we have to be careful, because p dot sum actually produces a sum
Of everything.
equals n dot float copy. P dot sum produces a
Yeah.
sums up all
So
of the
basically,
floats.
what he wants to do eventually is like do the sum, but do the sum for just the rows and not the entire matrix, right? That's what he wants to do, and that's why before we did like. So I'm not sure if this is actually correct syntax in Python, but probably what he wants to do is like something like this, I guess, or something like that. So that sum refers every time to the row.
And gives us a single number of just the summation of everything. So that's not the
That's
way we
probably
want
not
to
the
do it.
correct syntax, but
We want to simultaneously and in parallel divide all the rows by their respective sums.
yeah.
So what we have to do now is we have to go into documentation for torch.sum, and we can scroll down here to a definition that is relevant to us, which is where
Dimension, yeah.
provide an input array that we want to sum, but we also provide the dimension along which we want to sum.
Yeah,
And
exactly.
we want to sum up over rows, right? Now, one more argument that I want you to pay attention to here is
So that will be dimension 0.
the keep dim is false. keepdim is true, then the output tensor is of the same size as input, except of course the dimension along which you summed, which will become just 1.
Yeah.
But if you pass in keepdim as false, then this dimension is squeezed out. And so torch.sum not only does the sum and collapses dimension to be of size 1, but in addition it does what's called a squeeze, where it squeezes out that dimension. So basically what we want here is we instead want to do p.sum of sum axis. And in particular, notice that p.shape is 27 by 27.
Yeah.
So when we sum up across axis 0, then we would be taking the 0th dimension and we would be summing across it. So when keepdim is true, then this thing will not only give us the counts across along the columns, but notice that basically the shape of this is 1 by 27. We just get a row vector. And the reason we get a row vector here, again, is because we pass a 0 dimension. So this 0th dimension becomes 1. And we've done a sum, and we get a row. And so basically we've done the sum this way, vertically, and arrived at just a single 1 by 27 vector of counts. What happens when you take out keepdim is that we just get 27. So it squeezes out that dimension, and we just get
that's not ideal.
Of size 27.
Yeah, fair enough. So E equals p.sum, and then we want it in the first 0th dimension. Keepdim equals true.
Now, we don't actually want 1 by 27 row vector, because that gives us the counts or the sums across the columns.
Tensor object has no attribute shape. Does that make sense? That doesn't make sense.
We actually want to sum the other way, along dimension 1.
Yeah.
You see that the shape of this is 27 by 1, so it's a column vector. It's a 27 by 1 vector of counts.
Mm-hmm.
Okay? And that's because what's happened here is that we're going horizontally, and this 27 by 27 matrix becomes a 27 by 1 array. Now you'll notice, by the way, that the actual numbers of these counts are identical. And that's because this special array of counts here comes from Bigram statistics. And actually it just so happens by chance, because of the way this array is constructed, that the sums along the columns or along the rows, horizontally or vertically, is identical.
Yeah.
But actually what we want to do in this case is we want to sum across the rows horizontally. So what we want here is p.sum of 1 with keepdim true. 27 by 1 column vector. And now what we want to do is we want to divide by that. Now we have to be careful here again. Is it possible to take what's a p.shape you see here is 27 by 27? Is it possible to take a 27 by 27 array and divide it by what is a 27 by 1 array? Is that a
It is.
you can do? And whether or not you can perform this operation is determined by what's called broadcasting rules. So if you just search broadcasting semantics in Torch, you'll notice that there's a special definition for what's called broadcasting, that for whether or not these two arrays can be combined in a binary operation like division. So the first condition is each tensor has at least one dimension, which is the case for us. And then when iterating over the dimension sizes, starting at the trailing dimension, the dimension sizes must either be equal, one of them is 1, or one of them does not exist. Okay, so let's do that. We need to align the two arrays and their shapes, which is very easy because both of these shapes have 2 elements, so they're aligned. Then we iterate over from the right and going to the left. Each dimension must be either equal, one of them is a 1, or one of them does not exist. So in this case, they're not equal, but one of them is a 1, so this is fine. And then this dimension, they're both equal, so this is fine. So all the dimensions are fine, and therefore this operation is broadcastable. So that means that this operation is allowed. And what is it that these arrays do when you divide 27 by 27 by 27 by 1? What it does is that it takes this dimension 1 and it stretches it out. It copies it to match 27 here in this case. So in our case, it takes this column vector, which is 27 by 1, and it copies it 27 times to make these both be 27 by 27 internally. You can think of it that way. And so it copies those counts, and then it does an element-wise division.
So if you would do matrix manipulations by hand, this is something that you would do as well.
We want to divide by then on every single one of these columns in this matrix. So this actually we expect will normalize every single row. And we can check that this is true by taking the first row, for example, and taking its sum. We expect this to be 1, because it's not.
And it should indeed be. So again, with 1, what we expect again, so we calculated the probability, right? So with probability, what you always know is that it has to equal to 100%, which is 1.
Normalized. And then we expect this now, because if we actually correctly normalize all the rows, we expect to get the exact same result here. So let's run this. The exact same result. So this is correct.
I'm still getting some different results than he has. Like again, I made a mistake somewhat. I'm not sure where, because the seed value is the same. Maybe due to the fact that I removed the generator that was initialized earlier. I'm not getting the same result due to that. Just want to check something out. It shouldn't matter. Does it? No, it doesn't matter. It shouldn't matter. But I really cannot be bothered right now figuring out why that is, but
So
it's fine.
To scare you a little bit, you actually have to I basically encourage you very strongly to read through broadcasting semantics, and I encourage you to treat this with respect. And it's not something to play fast and loose with. It's something to really respect, really understand, and look up maybe some tutorials for broadcasting and practice it, and be careful with it, because you can very quickly
Note to self, go over it later.
You see how here we have p dot sum of 1, keep them as true. The shape of this is 27 by 1. Let me take out this line just so we have the n, and then we can see the counts. And we can see that this is all the counts across all the rows, and it's 27 by 1 column vector, right? Now, suppose that I tried to do the following, but I erase keep them as true here. What does that do? If keep them is not true, it's false.
And then it will squeeze it out, and then you will get an error
Then
probably.
remember, according to documentation, it gets rid of this dimension. It squeezes it out. So basically we just get all the same counts, the same result, except the shape of it is not 27 by 1, it's just 27. The 1 disappears. But all the counts are the same. So you'd think that this, divide that, would work. First of all, can we even write this? And will it is it even expected to run? Is it broadcastable? Let's determine if this result is broadcastable. P dot sum at 1 is shape, is 27. This is 27 by 27. So 27 by 27 broadcasting into 27. So now, rules of broadcasting, number 1, align all the dimensions on the right, done. Now iteration over all the dimensions starting from the right, going to the left. All the dimensions must either be equal, one of them must be 1, or one of them does not exist. So here they are all equal. Here the dimension does not exist. So internally what broadcasting will do is it will create a 1 here, and then we see that one of them is a 1, and this will get copied, and this will run, this will broadcast.
Mm-hmm.
Okay, so you'd expect this to work, because we are this broadcast, and this, you can divide this. Now if I run this, you'd expect it to work, but...
For real, props to Andre about how he goes into all the little semantics that go on with matrix manipulations and how PyTorch handles it in the background as well. I noticed this in the first video as well, where we went over like manually backpropagating the neurons and the weights and the gradients for them. Like, the way he explains things is like, this is one of the best. This guy has a talent for making tutorials.
You actually get garbage. You get a wrong result because this is actually a bug. This keep dim equals true makes it work. This is a bug. In both cases, we are doing the correct counts. We are summing up across the rows, but keep dim is saving us and making it work. So in this case, I'd like to encourage you to potentially pause this video at this point and try to think about why this is buggy and why the keep dim was necessary. Okay. So the reason to do for this is I'm trying to hint it here when I was sort of giving you a bit of a hint on how this works. This 27 vector, internally inside the broadcasting, this becomes a 1 by 27. And 1 by 27 is a row vector, right? And now we are dividing 27 by 27 by 1 by 27, and Torch will replicate this dimension. So basically...
And our y were the different
we'll take this row vector
characters.
and we'll copy it vertically now. 27 times, so the 27 by 27 aligns exactly, and element-wise divides. And so basically what's happening here is we're actually normalizing the columns instead of normalizing the rows.
Yeah.
So you can check that what's happening here is that p at 0, which is the first row of p, dot sum, is not 1, it's 7. It is the first column, as an example, that sums to 1. So to summarize, where does the issue come from? The issue comes from the silent adding of a dimension here, because in broadcasting rules, you align on the right and go from right to left, and if the dimension doesn't exist, you create it. So that's where the problem happens. We still did the counts correctly. We did the counts across the rows, and we got the counts on the right here as a column vector. But because the keep dims was true, this dimension was discarded, and now we just have a vector 27. And because of broadcasting the way it works, this vector of 27 suddenly becomes a row vector. And then this row vector gets replicated vertically, and then every single point we are dividing by the by the count in the opposite direction. So so this thing just doesn't work. This needs to be keep dims equals true in this case. So then we have that p at 0 is normalized. And conversely, the first column you'd expect to potentially not be normalized. And this is what makes it work. So pretty subtle, and hopefully this helps to scare you. That you should have respect for broadcasting, be careful, check your work, and understand how it works under the hood, and make sure that it's broadcasting in the direction that you like. Otherwise, you're going to introduce very subtle bugs, very hard to find bugs, and just be careful. One more note on efficiency.
Yes, sir.
We don't want to be doing this here because this creates a completely new tensor that we store into P. We prefer to use in-place operations if possible. So this would be an in-place operation. It has the potential to be faster. It doesn't create new memory. under the hood. And then let's erase this. We don't need it. And let's also just do fewer, just so I'm not wasting space. Okay, so we're actually in a pretty good spot now. We trained a Bigram language model, and we trained it really just by counting how.
It's not really training, right? It's pure probability and statistics from the data set that we have. I guess it is sort of training, but I get what he means.
Frequently any pairing occurs, and then normalizing so that we get a nice probability distribution. So really these elements of this array P are really the parameters of our Bigram language model, giving us and summarizing the statistics of these bigrams. So we train the model, and then we know how to sample from the model. We just iteratively sample the next character and feed it in each time and get the next character. Now what I'd like to do is I'd like to somehow evaluate.
Should I not have removed that? I should not have removed that.
The quality of this model. We'd like to somehow summarize the quality of this model into a single number. How good is it at predicting the.
Let's quickly. I want to make sure that the code I had before matches his.
I, and in I2S, we're going to reverse his dictionary.
I can remove that. Don't need that. Don't need that anymore.
So iterate over all the items. And just reverse that array. So I2S maps inversely from 0 to A, 1 to B, etc. So we'll need that. And then here's the code that I came up with to try to make this a little bit nicer. We create a figure, we plot n, and then we will just have 1, and I will call it a dot. Okay.
Oh my god, is that the issue I had all the time? If it is, then.
Let me swing this over here. Now, one more thing that I would like to do is I would actually like to make this special character have position 0. And I would like to offset all the other letters off. I find that a little bit more pleasing. So we need a +1 here so that the first character, which is A, will start at 1. So S to I will now be A.
Yeah.
1 and dot is 0. And I2S, of course, we're not changing this because I2S just creates a reverse mapping, and this will work fine. So 1 is A, 2 is B, 0 is dot.
Yeah, that works.
So we reverse that. Here, we have a dot and a dot. This should work fine. Make sure I start at zeros. Count.
ix2, ix1, and yes.
And then here we don't go up to 28, we go up to 27.
Yeah.
And this should just work. Okay. So we see that dot dot never happened. It's at 0 because we don't have empty words. Then this row here now is just very simply the counts for all the first letters. So J starts a word, H starts a word, I starts a word, etc. And then these are all the ending characters. And in between we have the structure of what characters follow each other. So this is the counts array of our entire dataset. So now these are the counts. And now what we'd like to do is we'd like to basically sample from this. Since these are the raw counts, we actually have to convert this to probabilities. So we create a probability vector. So we'll take n of 0, and we'll actually convert this to float first. Okay, so these integers are converted to floating point numbers. And the reason we're creating floats is because we're about to normalize these counts. So to create a probability distribution here, we want to divide. We basically want to do p divide p dot sum. And now we get a vector of smaller numbers, and these are now probabilities. So of course, because we divided by the sum of p now is 1. So this is a nice proper probability distribution. It sums to 1, and this is giving us the probability for any single character to be the first character of a word. So now we can try to sample from this distribution. To sample from these distributions, we're going to use Ortec multinomial, which I've pulled up here. The element in the
Yes.
and now index would be just the number 13.
Let me double check this once more because I want to make sure that I get the same results as he does. But the weird part was that I didn't get the same results, which is a bit weird, right? But again, I get 3 and not 13, which is so weird though. Torch and multinomial. The only thing that I could imagine again is that something in multinomial potentially changed and how it works in the background, and that's the reason why I get different results. But in regards to the manual seed, it shouldn't be different. Yeah, let me quickly go to the toilet. Be right back. And let me mute my mic. Also very nice, right? Also, in the meantime, I'm going to grab some coffee because I still am and will be an ITer, like a computer scientist. So my fuel is coffee. So be right back. Alright, I have my coffee again. Let's put on the air conditioning because it's getting hot outside. Alright, I have my coffee. We can continue.
And of course, we can map the I to S of IX to figure out exactly which character we're sampling here. We're sampling M. So we're saying that the first character is M in our generation.
I keep being surprised by this, you know, like for some reason. His random generator with the same manual seed gets a different result. That is so interesting to me. I don't know why, but there is something with that, and I don't know what. Let me quickly check if everything is still up to date here. I think it is, but yeah, everything seems fine. Timestamps, let that timestamps very quickly. Yeah, I quickly want to compare something. So upload. Okay, so for example, I do use AI sometimes, right? And for the reason of not being bothered of doing it myself, I'm like, yeah, compare those two and just tell me where the issue is at. There's a lot of I will continue in a short while. But the fiance asked me something, so I had to reply to her. Very important.
And just looking at the row here, M was drawn, and we can see that M actually starts a large number of words. M started 2,500 words out of 32,000 words. So almost a bit less than 10% of the words start with M. So this was actually fairly likely.
I think AI is wrong here.
Character to draw. So that would be the first character of our word.
Replacement true b equals 1. So what he does is I did it like that. But that can't be the issue, right? Yeah, that's fine. P-normalized sum. What we do? B equals bx. So we don't need that anymore because b is initialized. Yeah, it's interesting. Even AI says like you should get the same output, but the only difference here is like yeah. So AI says the reason that it could be different has indeed to do with the multinomial, what I thought. Like what it says, multinomial, even with the same seed, it picks something different. In your case, it happens to pick the index for C. With the correct normalization plus the exact same seed, the dynamic usage of first sample will start with M and the full first name will more or something similar. Yeah, but it's not a broken P, right? Like it should give the same, but it's fine. At least we now have this. At least we now have this. So let's just continue from where we left off.
Okay, so we're actually in a pretty good spot now. We trained a Bigram language model, and we trained it really just all these probabilities that we previously used for counting. This array P are really the parameters of our Bigram language model, giving us and summarizing the statistics of these bigrams.
Yeah.
So we train the model, and then we know how to sample from the model. We just iteratively sample the next character and feed it in each time and get a next character. Now what I'd like to do is I'd like to somehow evaluate the quality of this model. We'd like to somehow summarize the quality of this model into a single number. How good is it at predicting the training set? And as an example, so in the training set, we can evaluate now the training loss, and this training loss is telling us about sort of the quality of this model in a single number, just like we saw in micrograd. So let's try to think through the quality of the model and how we would evaluate it. Basically what we're going to do is we're going to copy paste this code that we previously used for counting.
Sure, let's do that. Why not?
Okay. And let me just print these bigrams first. We're going to use f-strings, and I'm going to print character 1 followed by character 2. These are the bigrams. And then I don't want to do it for all the words, just do the first 3 words. So here we have Emma, Olivia, and Ava bigrams. Now what we'd like to do is we'd like to basically look at the probability that the model assigns to every one of these bigrams. So in other words, we can look at the probability, which is summarized in the matrix P.
Yeah.
And then we can print it here as probability. And because these probabilities are way too large, let me percent or column and 4f to truncate it a bit. So what do we have here?
Probability 0.4f. Yeah.
Right? We're looking looking at the probabilities that the model assigns to every one of these bigrams in the dataset. And so we can see some of them are 4%, 3%, etc. Just to have a measuring stick in our mind, by the way, we have 27 possible characters or tokens, and if everything was equally likely, then you'd expect all these probabilities to be 4% roughly. So anything above 4% means that we've learned something useful from these bigram statistics. And you see that roughly some of these are 4%, but some of them are as high as 40%, 35%, and so on. So you see that the model actually assigned a pretty high probability to whatever's in the training set. And so
Interesting.
that's a good thing. Basically, if you have a very good model, you'd expect that these probabilities should be near 1, because that means that your model is correctly predicting what's going to come next, especially in the training set where you trained your model. So now we'd like to think about how can we summarize these probabilities into a single number that measures the quality of this model.
So how could we summarize all these probabilities to get the quality of the model?
Now, when you look at the literature into maximum likelihood estimation and statistical modeling and so on, you'll see that what's typically used here is something called the likelihood. And the likelihood is the product of all of these probabilities.
Yeah.
And so the product of all of these probabilities is the likelihood, and it's really telling us about the probability of the entire data set assigned by the model that we've trained. And that is a measure of quality. So the product of these should be as high as possible when you are training the model and when you have a good model. Your product of these probabilities should be very high. Now, because the product of these probabilities is an unwieldy thing to work with, you can see that all of them are between 0 and 1. So your product of these probabilities will be a very tiny number. So for convenience, what people work with usually is not the likelihood, but they work with what's called the log likelihood.
So logarithmic scaling.
The product of these is the likelihood. To get the log likelihood, we just have to take the log of the probability. And so the log of the probability here, I have the log of x from 0 to 1. The log is you see here, monotonic transformation of the probability, where if you pass in 1...
This is, by the way, what I've done with the transformer model for my price prediction transformer. Is basically what I do is with my dataset, everything that I've done, everything that is put into it, I grab the logarithm of that, where it's indeed scaled between 0 and 1, to normalize how for different assets basically behave. So for example, the S&P has like obviously less volatility than the Nasdaq. So if we would like logarithmically put in the candles, like programmatically put in the candles in a logarithmic way, we would have a scaled value where the neural network could learn based just on the numbers and the patterns in those numbers instead of hard code remembering, alright, if we have a candle that's 27,000 or something like that, that will then have the same result for the ES with, for example, 4,300.
Get 0. So probability 1 gets you log probability of 0. And then as you go lower and lower probability, the log will grow more and more negative until all the way to negative infinity at 0. So here we have a log prob, which is really just a torch.log of probability. Let's print it out to get a sense of what that looks like. Log prob, also 0.4f.
So what I don't like what I would do, he doesn't use camel casing, etc. Like coming from C#, I always would use camel casing.
So as you can see, when we plug in numbers that are very close, some of our higher numbers, we get closer.
But it's a tutorial, so it is forgiven.
And then if we plug in very bad probabilities, we get more and more negative numbers.
Plus, I'm actually not sure what the code conventions are for Python. Like, perhaps normal casing in, like, scoped variables is fine. I know that that camel casing is basically like the requirement for variables in C#, right? So I'm not sure what the rules, what the code conventions are for Python.
That's bad. So, and the reason we work with this is for large extent convenience, right? Because we have mathematically that if you have some product, A times B times C, of all these probabilities, right? The likelihood is the product of all these probabilities. Then the log of these is just log of A plus log of B
Yeah.
plus log of C. If you remember your logs from your high school or undergrad and so on.
Yeah. So this is basic. It's not algebra. I'm not actually sure on what topic it falls, but this is indeed like so. For example, my high school, I had got something called Nature and Technic, the profile that I studied, and indeed with Math B, it's called like Math D. This was indeed like something that you learned, like and then you were wondering, oh, when would I ever use it? Well, you would use it in cases like this if you get into this field of programming, and especially quant places and AI right now. Like with scaling, it helps a lot.
The product of probabilities, the log likelihood is just the sum of the logs of the individual probabilities. So log likelihood starts at 0, and then log likelihood here we can just accumulate simply. And then at the end we can print this. Print the log likelihood.
And then it should be near 1.
Maybe you're familiar with this. So log likelihood is negative 38.
Negative 38.
Okay.
You see, so where I was also like, this should get closer to 1. That was funny.
Now, we actually want, so how high can log likelihood get? It can go to 0. So when all the probabilities are 1, log likelihood will be 0. And then when all the probabilities are lower, this will grow more and more negative. Now, we don't actually like this because what we'd like is a loss function. And a loss function has the semantics that low is good because we're trying to minimize the loss.
Yeah.
So we actually need to invert this. And
so you could get the absolute values, right?
The negative log likelihood. Negative log likelihood is just negative of the log likelihood. These are F strings, by the way. If you'd like to look.
So there are different ways that you could do this. So you could also get just the absolute value. Inversing it would be quick.
Negative log likelihood equals.
But yeah.
So negative log likelihood now is just the negative of it. And so the negative log likelihood is a very nice loss function because the lowest it can get is 0. And the higher it is, the worse off.
Negative log likelihood. Again, I just copy whatever he's doing because it's the tutorial, right? Maybe I should not invert it again.
The predictions are that you're making. And then one more modification to this that sometimes people do is that for convenience, they actually like to normalize by, they like to make it an average instead of a sum.
Yeah.
And so here, let's just keep some counts as well. So n plus equals 1 starts at 0. And then here, we can have sort of like a normalized log likelihood.
So basically what the normalized negative log likelihood is that on average it calculates, okay, for every prediction that we did, we are off by X amount, the average, right? So instead of our whole prediction is bad with 38 in a loss function, that's for the entire word, but with the neural net where we predict characters, it's better to get the, well, what you already mentioned.
which is normal.
So let's quickly do that as well. So n plus equals 1. We can do the same for the log likelihood, right? So if we already divide well, if we already do log likelihood divide here by n, then we get the same result. Then we have like the log likelihood itself and the negative log likelihood. And this basically means like, alright, this is the loss function for each character instead of the whole word.
Then we will sort of get the average log likelihood. So this would be usually our loss function here. This is what we would use. So our loss function for the training set assigned by the model is 2.4. That's the quality of this model. And the lower it is, the better off we are. And the higher it is, the worse off we are. And the job of our training is to find the parameters that minimize the negative log likelihood loss. And that would be like a high quality model. Okay, so to summarize, I actually wrote it out here. So our goal is to maximize likelihood, which is the product of all the probabilities.
Let me quickly grab some water, so I'll be back. By the way, I still have my headset on, so I can still keep talking. So to sum up again, why I'm doing this right now. So even though that I have worked with neural networks since 2016, due to the fact that I've been working in the quant space for the past 4 years, I've been more focused for the past 4 years on, let's say, low latency code, etc., and low cyclomatic complexity, low time complexity, all those kinds of things. So this is basically just refreshing and just streaming basically how I am regaining the knowledge of PyTorch.
Assigned by the model. And we want to maximize this likelihood with respect to the model parameters. And in our case, the model parameters here are defined in the table. These numbers, the probabilities, are the model parameters, sort of in our Bigram language model so far. But you have to keep in mind that here we are storing everything in a table format, the probabilities. But what's coming up as a brief preview is that these numbers will not be kept explicitly, but these numbers will be calculated by a neural network. So that's coming up. And we want to change and tune the parameters of these neural networks.
Yeah.
We want to change these parameters to maximize the likelihood, the product of the probabilities. Now, maximizing the likelihood is equivalent to maximizing the log likelihood, because log is a monotonic function. Here's the graph of log, and basically all it is doing is it's just scaling your, you can look at it as just a scaling of the loss function. And so the optimization here and here are actually equivalent, because this is just scaling. You can look at it that way. And so these are two identical optimization problems. Maximizing the log likelihood is equivalent to minimizing the negative log likelihood. And then in practice, people actually minimize the average negative log likelihood to get numbers like 2.4. And then this summarizes the quality of your model. And we'd like to minimize it and make it as small as possible. And the lowest it can get is 0. And the lower it is,
What 0 basically means is that so you have your test set, right? So in this case, it's our names.txt, which is 32,000 plus names. Basically, what 0 means is that there's no difference from a name in that data set. So you are 100% sure that the prediction that you have is correct. The issue with this is that once you train a neural network, and with something like makemore, you want to make more names. But the issue with that is that if you get to 0, that means that you're not making more names. You are actually generating all those names over and over again, probably. That's what I expect. So, and that's what we call in data science with neural networks, etc. We call that overfitting. So your network is trained too much to a certain paradigm where doesn't it doesn't take into account like uh, new data from it, and that's why we also most of the times work with split data tests, where we split our data test into 80% training, 20% testing, etc.
Better off your model is because it's assigning high probabilities to your data. Now let's estimate the probability over the entire training set just to make sure that we get something around 2.4. Let's run this over the entire. Oops. Let's take out the print statement as well.
2.4. Interesting.
Okay, 2.45 or the entire training set. Now what I'd like to show you is that you can actually evaluate the probability for any word that you want. Like for example, if we just test a single word, Andre, and bring back the print statement, then you see that Andre is actually kind of like an unlikely word. Like,
I actually wonder what my hold on. I actually wonder what the probabilities of my name in the American dataset. Like the dataset that's used is from American names. So for WN doesn't matter. Capital casing probably matters because it's trained on lower capitals. Wow! Apparently my name in would be a very likely name in America. That's interesting. Like my name compared to the whole data set is actually very likely. I didn't expect that because this name is actually a very Dutch word. Like it's wow. That's actually fun. What happens if I doubt it? Okay, that's interesting. That's funny. That's funny. Like one of the most Dutch names is actually like very likely in the American data set.
on average, we take 3 log probability to represent it, and roughly that's because EJ apparently is very uncommon as an example.
That's so hilarious.
Now, think through this. When I take Andre and I append Q, and I test the probability of it, Andre Q,
Probability would
we actually
probably
get
yeah.
infinity. And that's because JQ has a 0% probability according to our model. So the log likelihood, so the log of 0 will be negative infinity. We get infinite loss. So this is kind of undesirable, right? Because we plugged in a string that could be like a somewhat reasonable name. But basically what this is saying is that this model is exactly 0% likely to predict this name. And our loss is infinity on this example.
I would imagine that if so, for example, if you would have Chinese names or something like that, or Indian names, because like let's just say Asian names, right? Asian names. So from the east side of the world. Since it's an American data set, it will be like more Western. So I would assume that there might be a lot of names that actually would say like, oh yeah, the possibility, the probability of that name actually existing is 0
And really what
or
this means
infinity in
is
this
that
case.
J is followed by Q 0 times. Where's Q? JQ is 0. And so JQ is 0% likely. So it's actually kind of gross, and people don't like this too much. to fix this, there's a very simple fix that people like to do to sort of like smooth out your model a little bit, and it's called model smoothing. And roughly what's happening is that we will add some fake counts. So imagine adding.
I would imagine if you add fake counts, you would have to remove some probability from, for example, the highest occurring number, because otherwise you would get above the probability of 1, which is weird, right?
Count of 1 to everything. So we add a count of 1 like this, and then we recalculate the probabilities.
But then you get a probability of higher than 1. I mean, it's possible, but it's a bit weird. But sure. Oh wait, it actually doesn't matter, because like we add a count, like we have the array, then we add 1 to it, and then we get the probability of everything. So yeah, no, it does. So the probability remains 1. So that's fair enough. But we would expect that this one changes a little bit, you know.
And that's model smoothing. And you can add as much as you like. You can add 5, and that will give you a smoother model. And the more you add here, the more uniform model you're going to have. And the less you add, the more peaked model you're going to have, of course. So 1 is like a pretty decent count to add, and that will ensure that there will be no zeros in our probability matrix P.
So for your information, what this basically means, so we have a data set of like 32,000 names, right? So the only thing you do with +1 is that you basically add for every strange thing to every name you add that that character that doesn't exist.
And so this will of course change the generations a little bit. In this case it didn't, but in principle it could. But what that's going to do now is that nothing will be infinity unlikely. So now our model will predict some other probability, and you see that JQ now has a very small probability. So the model still finds it very surprising that this.
Let's quickly. I wonder if my name changed now. I doubt. So this is also interesting. I expect, yeah, it doesn't know J because it's capital sensitive, right? Yeah. Just because we, okay, hold on. So the probability of my name with the model smoothing, did that actually just, okay, so 1.974 for 1. And if we add model smoothing, if we smooth the model, my name is actually getting a little bit more likely. I mean, maybe that makes sense, right? Because since the dataset is American, and even though the Netherlands is Western as well, like a few more combinations could add up. I could imagine that there are some names in Dutch where that would occur.
Was a word or a bigram, but we don't get negative infinity. So it's kind of like a nice fix that people like to apply sometimes, and it's called model smoothing. Okay, so we've now trained a respectable bigram character level language model, and we saw that we both sort of trained the model by looking at the counts of all the bigrams and normalizing the rows to get probability distributions. We saw that we can also then use those parameters of this model to perform sampling of new words. So we sample new names according to those distributions. And we also saw that we can evaluate the quality of this model. And the quality of this model is summarized in a single number, which is the negative log likelihood. And the lower this number is, the better the model is, because it is giving high probabilities to the actual next characters in all the bigrams in our training set.
No.
So that's all well and good, but we've arrived at this model explicitly by doing something that felt sensible. We were just performing counts, and then we were normalizing those counts. Now what I would like to do is I would like to take an alternative approach. We will end up in a very, very similar position, but the approach will look very different. because I would like to cast the problem of Bigram character level language modeling into the neural network framework. And in the neural network framework, we're going to.
So how would he do this, right? So I know that in the tutorial he's going to work towards like the tokenizer, etc. of ChatGPT, like creating Nano GPT. A way that you could do this, if you would use a multi-layer perceptron, is that you have one input neuron, which is like a character. Then we have like the 26 then we have 27 neurons for like the alphabet, and then the dot for the beginning and the end, and then basically retrain it every time. And that's not a multi-layer perceptron, of course, because we have one layer. So what you could do is like add 2 layers of 27 that would predict like the next uh, character, and then maybe the second character as well, which like would predict 2 potential next characters. Like, yeah, that might be the way that he wants to go.
Approach things slightly differently, but again, end up in a very similar spot. I'll go into that later. Now, our neural network is going to be still a Bigram character level language model. So it receives a single character as an input. Then there's neural network that waits for some parameters W.
I told you this. I told you this. So again, he puts in a single character, and then we have the weights towards the other, uh, well, things like the other characters plus the dot, what we pre-described, and those weights are basically just the probabilities that are in here. That's the route he probably wants to go. And if he wants to do it with a multi-layer perceptron, he will put one layer after it as well.
And it's going to output the probability distribution over the next character in a sequence. So it
Yeah.
can make guesses as to what is likely to follow this character that was input to the model. And then in addition to that, we're going to be able to evaluate any setting of the parameters of the neural net because we have the loss function, the negative log likelihood. So we're going
Yeah.
to take a look at its probability distributions, and we're going to use the labels, which are basically just the identity of the next character in that bigram, the second character. So knowing what second character actually comes next in the bigram allows us to then look at how high of a probability the model assigns to that character, and then we of course want the probability to be very high. And that is
So
another way of
in
saying.
that case, so maybe he does it a little bit different. I said like we would have like a multi-layer perceptron, and then would have one next output, which would be a character. But what also would be able is that you have the multi-layer perceptron instead of having one output neuron, which would display the character. In that case, what you would have probably is like the 27 outputs, and then um, have which basically would be like dot and then A to Z, and then which has the highest likelihood, that would be the next character. And then to generate a name, we would re we would put the highest likely output character in the neural network again until the highest likely output will be a dot, which will be an ending of a name, right? I think that he's going that route instead of the route that I chose.
Okay, that the loss is low. So we're going to use gradient-based optimization then to tune the parameters of this network because we have the loss function and we're going to minimize it. So we're going to tune the weights so that the neural net is correctly predicting the probabilities for the next
Yeah.
character. So let's get started.
I really wonder which type of architecture is going to use for like the hidden layers. Like if he's indeed going for like a base hit multi-layer perceptron, like maybe a multi-layer perceptron is a little bit overkill, yeah. Like in theory, you could just have input layer, output layer with the weights in between. But with the multi-layer perceptron, you might be able to get uh, better results. The training would be a little bit different though, but
First thing I want to do is I want to compile the training set of this neural network, right? So create the training set of all the bigrams. Okay. And here, I'm going to copy paste this code, because this code iterates over all the bigrams. So here we start with the words, we iterate over all the bigrams, and previously, as you recall, we did the counts. But now we're not going to do counts, we're just creating a training set. Now this training set will be made up of two lists. We have the inputs and the targets.
Yeah, the probability.
And these bigrams will denote XY. Those are the characters, right?
Yeah.
And so we're given the first character of the bigram, and then we're trying to predict the next one. Both of these are going to be integers. So here, we'll take x's that append is just x1, y's that append ix2. And then here,
Fair enough. Okay.
we actually don't want lists of integers. We will create tensors out of these. So x's is torch.tensor of x's, and y's is torch.tensor of y's.
Yeah, so he went over this basically in his first video, like why you do not want to work with lists and convert it to tensors. Like, of course, everything in Torch works with tensors, but the whole reasoning behind it is that mathematics, basically, it's more arithmetics on tensors is more optimized than doing it on lists. That's the whole idea, basically, from it. If I remember correctly.
And then we don't actually want to take all the words just yet, because I want everything to be manageable. So let's just do the first word, which is Emma. And then it's clear what these x's and y's would be. Here, let me print character 1, character 2, just so you see what's going on here. So the bigrams of these characters is dot .e, em, mm, ma, a dot. So this single word, as I mentioned, has 1, 2, 3, 4, 5 examples for our neural network. There are 5 separate examples in Emma, and those examples are summarized here. When the input to the neural network is integer 0, the desired label is integer 5, which corresponds to e. When the input to the neural network is 5, we want its weights to be arranged so that 13 gets a very high probability. When 13 is put in, we want 13 to have a high probability. When 13 is put in, we also want 1 to have a high probability. When 1 is input, we want 0 to have a very high probability. So there are 5 steps.
So, and if we convert this, like, this again goes back to our matrix, our two-dimensional array here, right, with the bigrams. So basically when he says 1, what he means is, and that's what you see with the tensor XS, where we end at 1, that's A. So that's A dot.
Separate input examples to a neural net in this data set.
So, sorry, I explained it wrongly. So basically what 1, 0 means is that it is an 1 is an A, but the result is, okay, the dot is the next one. So hence 0.
I wanted to add a tangent of a note of caution to be careful with a lot of the APIs of some of these frameworks. You saw me silently use torch.tensor.
That's, by the way, quickly, just ensure, right, that we have the same results as he has. We should have. XS is not defined. Didn't run it. That's okay. So we got the same results as he
polynomial
has.
speed, and the output looked right. But you should be aware that there's actually two ways of constructing a tensor. There's a torch.lowercase tensor, and there's also a torch.capital tensor class, which you can also construct. So you can actually call both. You can also do torch.capital tensor, and you get an x's and y's as well. So that's not confusing at all. There are threads on what is the difference between these two. And unfortunately, the docs are just like not clear on the difference. And when you look at the docs of lowercase tensor, construct tensor with no autograd history by copying data. It's just like it doesn't make sense. So the actual difference, as far as I can tell, is explained eventually in this random thread that you can Google. And really, it comes down to, I believe.
So what I would assume is that one is like maybe a factory pattern, and one is like real a constructor that just takes over everything, right?
That where is this?
That's what I
It
would assume, but
refers the D type, the data type automatically, while
yeah,
torch.tensor just returns a float tensor. I would recommend to stick to torch.lowercase tensor.
yeah. So that's basically what I meant. Like the lowercase tensor will like use some kind of factory pattern potentially. Like I'm not going into the PyTorch library. Probably and then that it like copies over indeed the data type, and like when you use the normal the capital T, where it will like use the default tensor, where it uses floating types, which is often used in data science.
So indeed, we see that when I construct this with a capital T, the data type here of x's is float 32. But torch.lowercase tensor, you see how it's now x.d type is now integer.
Yeah.
So it's advised that you use lowercase t, and you can read more about it if you like in some of these threads.
So basically, in short, if you want to keep the same data type that your actual objects have, you just use lowercase. Okay.
Basically, I'm pointing out some of these things because I want to caution you, and I want you to get used to reading a lot of documentation and reading through a lot of Q&As and threads like this. And some of this stuff is unfortunately not easy and not very well documented. And
Again, the way that Andre does tutorials, it's amazing. Like he forces you to sometimes pause and think for yourself and go your own route about it. But also what he just mentions, like getting familiar with what we did earlier with the multinomial, like that you have to read through it on how it works and what it can do. Like in real world examples, this is what we do, right? Like we have an issue, and then we don't know how to solve it, and then we have to look into the documentation. So he's forcing you to kind of apply real world situations to it.
what we want here is integers, because that's what makes sense. And so lowercase tensor is what we are using. Okay, now we want to think through how we're going to feed in these examples into a neural network.
Okay, now I really wonder if we're going to get into what I mentioned, that like he is indeed going to use a multi-layer perceptron or like a single layer or something like
It's
that.
not quite as straightforward as plugging it in, because these examples right now are integers. So there's like a 0, 5, or 13. It gives us the index of the character, and you can't just plug an integer index into a neural net. These neural nets, right, are sort of made up.
I mean, in theory you can, but you would have to eventually you would have to uh, you have to figure out what was the value of that index value. Like we know what it is within our P, right? But like within our char set, but
Of these neurons, and these neurons have weights. And as you saw in micrograd, these weights act multiplicatively on the inputs, wx plus b, there's 10h's, and so on. And so it doesn't really make sense to make an input neuron take on integer values that you feed in and then multiply with weights. So instead, a common way of encoding integers is what's called one-hot encoding. In
yeah.
one-hot encoding, we take an integer like 13, and we create a vector that is all zeros except for the 13th dimension, which we turn to a 1. And then that vector can feed into a neural net. Now, conveniently, PyTorch actually has something called the one-hot class.
That's actually an interesting take on it, because that means that eventually what we will have is that our input vector for a neural network would be like 26 large, due to the fact with like if we input a dot and then we have A to Z. That is a way to go.
Um, Function inside torsion and functional. It takes a tensor made up of integers. Long is an integer, and it also takes a number of classes, which is how large you want your tensor, your vector.
So I assume that he would choose 26 here. Because we can, like the way we have done the bigram so far is like that we go from A to Z and then we have a dot for the start and the finish, right?
To be. So here, let's import torch dot and then dot functional SF. This is a common way of importing it. And then let's do f dot one hot, and we feed in the integers that we want to encode. So we can actually feed in the entire array of x's, and we can tell it that num classes is 27.
27. Ah, yeah, 27 because the alphabet's 26. Fair enough. Potato, potato, it's the same thing. I was correct though on this.
It may have guessed that it's only 13, and would.
Yeah, and then the output would be the same, right? So input would be something. Yeah, we will just follow what he's doing. I can screw around with myself, but
So this is the one hot. Let's call this x inc for
X encoding. Yeah, fair enough. But then we also have Y encoding, which will be the same. Because those are our validations, right?
And then we see that x encoded shape is 5 by 27, and we can also visualize it.
Does that shape make sense? I'm thinking about it. Like, I know he's going to explain it, like 27, but why would he Oh, wait, that makes sense. Because we have like Emma, right? So Emma with the dot is like we have 5. Yeah, that makes sense.
That I am show of xing to make it a little bit more clear, because this is a little messy. So we see that we've encoded all the 5 examples into vectors. We have 5 examples, so we have 5 rows, and each row here is now an example into a neural net.
Yeah.
And we see that the appropriate bit is turned on as a 1, and everything else is 0.
And that's why, like, these are both amps, right? Because we have our A to Z and our dot, and then we have like E, M, A. That's the. Oh, hold on. 0 was dot, so then we have E, M, M, A.
So here, for example, the 0th bit is turned on, the 5th bit is turned on, 13th bits are turned on for both of these examples, and then the first bit here is turned on. So that's how we can encode integers into vectors.
Yeah, and M is indeed 13.
And then these vectors can feed in to neural nets. One more issue to be careful with here, by the way, is let's look at the data type of X encoding. We always want to be careful with data types. What would you expect X encoding?
When looking at this, it would probably be int 32, right?
the data type to be. When we're plugging numbers into neural nets, we don't want them to be integers. We want them to be floating point numbers that can
Because
take on
if I'm looking at this, these are not floating pointers. These are integers, I
real
would say.
numbers. But the D type here is
Oh,
actually
in
a 64-bit
64.
integer. And the reason for that, I suspect, is that one hot received a 64-bit integer here, and it
This
invoked
is
it
basically the same with the lowercase tensor, right? So it will use like some form of factory pattern where it would take over the data type.
turned the same data type. And when you look at the signature of one hot, it doesn't even take a D type, a desired data type, of
Yeah.
the output tensor. And so we can't, in a lot of functions in Torch, we'd be able to do something like D type equals torch.float32, which is what we want.
So we would have to recast it indeed.
So instead, we're going to want to cast this
Yeah,
float like this.
makes sense. Yeah. And by the way, how I knew that it was an integer, not a float, was that before. So if we have this right, floating point numbers always have like the dot over there, uh, and integers don't. Like integers can't have the dot because they can't have decimal values.
So that these, everything is the same. Everything looks
Interesting fact for for floating point numbers, how they are calculated is like there's one bit that is set, I think, at the end bit to like indicate negative numbers or something like that. It's very interesting.
the same, but the D type is float32. And floats can feed into neural nets. So now let's construct our first neuron. This neuron will look at these input vectors. And as you remember from micrograd, these neurons basically perform a very simple function, wx plus b, where wx is a dot product.
Yeah.
So we can achieve the same thing here. Let's first define the weights of this neuron, basically. What are the initial weights at initialization for this neuron? Let's initialize them with torch.random. Torch.random is fills a tensor with random numbers drawn from a normal distribution.
Okay. If this one does not require a seed, and apparently it doesn't, we will get a different weight or different results than he has. Because before we were using like the manual seed generator.
And a normal
So
distribution has a probability density function like this. And so most of the numbers drawn from this distribution will be around 0, but some of them will be as high as almost 3 and so on. And very few numbers will be above 3 in magnitude. So we need to take a size as an input here. And I'm going to use size as to be 27 by 1.
So if he's using 27 by 1, that's it's probably the reason for like we have one dimension in the horizontal axis for like A to Z and then the dot, right? Because yeah, or oh wait. Yeah.
27 by 1, and then let's visualize W. So W is a column vector of 27 numbers.
Oh, yeah, due to the fact, so the dimension. Yeah, okay, so that's yeah, a column factor. Yeah.
And these weights are then multiplied by the inputs. So now to perform this multiplication, we can take X encoding and we can multiply it with W. This is a matrix multiplication operator in PyTorch. And the output of this operation is 5 by 1. The reason it's 5 by 1 is the following. We took X encoding, which is 5 by 27, and we multiplied it by 27 by 1. And in matrix
For real, matrix multiplication. When I had this, I think it was with games programming, the semester games program, where I had to learn matrix multiplication. It's I hated it so much, especially when you why we had to learn matrices, and especially three-dimensional matrices. I had to do like with generating our own computer vision driver, like our video settings driver, like on how rotational of objects is calculated. It's such a pain in the ass, but once you get the hang of it, it's quite fun.
multiplication,
I will be honest, like I don't know anymore how to do this by heart. I would have to refresh things like this.
Will become 5 by 1, because these 27 will multiply and add. So basically what we're seeing here, out of this operation, is we are seeing the 5 activations of this neuron on these 5 inputs. And we've evaluated all of them in parallel. We didn't feed in just a single input to the single neuron. We fed in simultaneously all the 5 inputs into the same neuron. And in parallel, PyTorch has evaluated the WX plus B, but here it's just WX, there's no bias. It has valued W times X for all of them.
I wonder why you would use a bias there. Maybe if you would like to create names with more letters like A, E, I, all those kinds of things.
Independently. Now, instead of a single neuron, though, I would like to have 27 neurons. And I'll show you in a second why I want
I think he's going to explain what I explained prior.
27 neurons.
Like so that we have like the input of 27 neurons, right? So from A to Z and then 1, and then the output will be also A to Z 1, and then with the probability. But he probably wants it due to the fact that he potentially already knows what's in the name already. But
So instead of having just a 1 here, which is indicating this presence of one single neuron, we can use 27. And then when W is 27 by 27, this will, in parallel, evaluate all the 27 neurons on all the 5 inputs.
yeah.
Giving us
So basically, what he recreated here is, in theory, this matrix, right? And what he probably wants to do eventually is calculate the probability that we have under here of the occurrences.
much better, much bigger result. So now what we've done is 5 by 27 multiplied 27 by 27, and the output of this is now 5 by 27. So we can see that the shape of this is 5 by 27. So what is every element here telling us, right? It's telling us for every one of 27 neurons.
Basically, what it is telling us is for Emma, so for her name, is what's the probability in this matrix. So EM, MM, MA, etc. For each letter.
What is the firing rate of those neurons on every one of those 5 examples? So the element, for example, 3, 13 is giving us the firing rate of the 13th neuron looking at the 3rd input.
Which in this case would be the M compared to 13, which is also M in the matrix. So you would expect, once it's trained, that this would give a very high neuron output. Or, yeah.
And the way this was achieved is by a dot product between the 3rd input and the 13th column of this W matrix here. Okay, so using matrix multiplication, we can very efficiently evaluate the dot product between lots of input examples in a batch and lots of neurons, where all of those neurons have weights in the columns of those W's. And in matrix multiplication, we're just doing those dot products in parallel. Just to show you that this is the case, we can take xenc and we can take the 3rd row, and we can take the W and take its 13th column, and then we can do xenc at 3, element-wise multiply with W at 13, and sum that up. That's WX plus B. Well, there's no plus B, it's just WX dot product. And that's this number.
Yeah.
So you see that this is just being done efficiently by the matrix multiplication operation for all the...
For real, in uni, what we had to do, so right now we have PyTorch and all those kinds of things, right? In uni, what we had to do as an assignment was literally create our own backend where all these matrix multiplications were done. Like, and it was such a hell to do that. And like then adding operator overloading to it and all those kinds of things. It was fun, but it was also hell for a lot of people.
And for all the output neurons of this first layer. Okay, so we fed our 27-dimensional inputs into a first layer of the neural net that has 27 neurons, right? So we have 27 inputs, and now we have 27 neurons. These neurons perform W times X. They don't have a bias, and they don't have a nonlinearity like tanh. We're going to leave them to be a linear layer. In addition to that, we're not going to have any other layers. This is going to be it. It's just going.
Okay, so he's not going to make a multi-layer perceptron. So what he probably is going to do is that we have a vector of 27 as input, a hidden layer of 27, and then an output of 27 as well for the next character probability.
Going to be the dumbest, smallest, simplest neural net, which is just a single linear layer. And now I'd like to explain what I want those 27 outputs to be. Intuitively, what we're trying to produce
Let's see if I was correct with my hypothesis.
here for every single input example is we're trying to produce some kind of a probability distribution for the next character in a sequence. And
There you go.
we have to come up with like precise semantics for exactly how we're going to interpret these 27 numbers that these neurons take on. Now, intuitively, you see here that these numbers are negative and some of them are positive, etc. And that's because these are coming out of a neural net layer initialized with these no.
Yeah, so he's correct here, obviously. Obviously, this guy for real in regards to tutorials, he's awesome. Like he's explaining things that I have forgotten from a few years ago so clearly. It's amazing. Like Andre, for real, thank you for doing this.
Distribution parameters. But what we want is we want something like we had here. Like each row here told us the counts, and then we normalize the counts to get probabilities. And we want something similar to come out of a neural net. But what we just
I literally explained this. While we were doing this, right, with the hot encoding, this is literally like, I already put the line here, but this is literally what I mentioned.
right now is just some negative and positive numbers.
It's good to know that still some knowledge has remained from doing things like this.
Now, we want those numbers to somehow represent the probabilities for the next character. But you see that probabilities, they have a special structure. They're positive numbers, and they sum to 1.
Yeah.
So that doesn't just come out of a neural net. And then they can't be counts because these counts are positive and counts are integers.
So probably what he's going to do is like the output layer is going to normalize it between 0 and 1, like I mentioned before, and then take the highest number out of that and then put that against our array or something like that, where the index is equal to the neuron.
So counts are also not really a good thing to output from the neural net. So instead, what the neural net is going to output and how we are going to interpret the 27 numbers is that these 27 numbers are giving us log counts, basically. So instead of giving us counts directly, like in this table, they're giving us log counts. And to get the counts, we're going to take the log counts and we're going to exponentiate them. Now,
That's
takes the following form.
It's interesting that he goes that route. I mean, yeah, it's one way to go with the output. But I think that going between 0 and 1 might actually be just as good. I mean, this is more like in your face. Like, alright, it's there. Like, you have to activate now if it's a very large number. And like, between 0 and 1 is more like a normalized output.
It takes numbers that are negative or they are positive. It takes the entire real line. And then if you plug in negative numbers, you're going to get e to the x, which is always below 1. So you're getting numbers lower than 1. And if you plug in numbers greater than 0, you're getting numbers greater than 1, all the way growing to the infinity. And this here grows to 0. So basically, we're going to take these numbers here.
But will you not get, like, if you indeed go, if you would go beyond the scope of a float size, and I don't know if this is possible during training, you might get like an overflow, so where the actual number is not correct anymore. So for example, if you hit the max, if the exponential value is greater than what's possible to fit in the memory that's allocated for a float, then it will restart itself, right? So you would get a really weird number. I'm not eventually with training you could get that shit out, but I wonder if we would encounter that during this tutorial.
And instead of them being positive and negative and all over the place, we're going to interpret them as log counts, and then we're going to element-wise exponentiate these numbers. Exponentiating them
Yeah.
gives us something like this. And you see that these numbers now, because they went through an exponent, all the negative numbers turned into numbers below 1, like 0.338. And all the positive numbers originally turned into even more positive numbers, sort of greater than 1. So like, for example, 7 is some positive number over here that is greater than 0. But exponentiated outputs here basically give us something that we can use and interpret as the equivalent of counts originally. So you see these counts here, 112, 7.
I wonder the scenario that I actually just pictured, if that is even possible, that would mean that random n would. Okay, okay, alright, it would not happen because random n will, as I look at it, like it is not giving very large numbers. But if it would have higher numbers, then yeah, that could give issues.
1, 1, etc. The neural net is kind of now predicting counts. And these counts are positive numbers. They can never be below 0, so that makes sense. And they can now take on various values depending on the set.
So let's see. Does torch.randomn actually give extremely high numbers? Doesn't look like it does it? No. It gives between 3 and -3 or something like that, it looks like. Or between 1 and -1. Yeah, 1 and -1. Okay, fair. Then it is okay. For things like that, you would have to look again on the documentation.
Of W. So let me break this down. We're going to interpret these to be the log counts. Another words for this, that is
Why would you call it logits?
often used, is so-called logits.
Logits.
These are logits, log counts. Then these will be.
Sometimes there are like things in the computer programming industry, like things like this logits. Like apparently that's a thing. I didn't know that. uh, it's interesting.
For the counts, logits exponentiated. And this is equivalent to the n matrix, sort of, the n array that we used previously.
Yeah, that's what I mentioned before.
This is the array of counts, and each row here.
So it's interesting that he goes this route. Like I had the same feeling that he would go this route. But it's nice. Like it's nice when you're trying to learn something again or relearn something that if you make a prediction and this is with programming in general, right? And programming is basically like just being very good at problem solving. So if he puts something in here, like okay, we might go this route. then I'm already thinking, okay, how would we solve this in another way? And my hypothesis was that he was indeed trying to recreate this matrix within the neural net.
Are the counts for the next character, sort of. So those are the counts, and now the probabilities are just the counts normalized. And so I'm not going to find the same, but basically I'm not going to scroll all over the place. We've already done this. We want to counts.sum along the first dimension, and we want to keep this as true. We went over this, and this is how we normalize the rows of our counts matrix to get our probabilities. So now these are the probabilities, and these are the counts that we have currently. And now when I show the probabilities, you see that every row here, of course, will sum to 1 because they're normalized. And the shape of this is 5 by 27. And so really what we've achieved is for every one of our 5 examples, we now have a row that came out of a neural net.
Yeah, so basically what you have is like Emma, right? And then below it you have the probability of the next character every time.
And because of the transformations here, we made sure that this output of this neural net now are probabilities, or we can interpret to be probabilities. So our WX here gave us logits, and then we interpret those to be log counts. We exponentiate to get something that looks like counts, and then we normalize those counts to get a probability distribution. And all of these are differentiable operations. So what we've done now is we are taking inputs.
Okay, so why it goes about differential operations is due to the fact with backpropagation, what you do is like you differentiate the result from what it was to then calculate the gradient, and then based on the gradient you can calculate your loss function and then adjust the weights every so slightly.
Differentiable operations that we can backpropagate through, and we're getting out
There you go.
probability distributions. So, for example, for the 0th example that fed in, right, which was the 0th example here was a one-hot vector of 0, and it basically corresponded to feeding in this example here. So we're feeding in a dot into a neural net. And the way we fed the dot into a neural net is that we first got its index, then we one-hot encoded it, then it went into the neural net, and out came this distribution of probabilities. And it's...
I really like, again, how Andre goes through this step by step. Like, I was already a little bit too rapid about this earlier on, but the way he works to the conclusion, it's so easy to learn if you're totally new to this stuff.
shape is 27. There's 27 numbers. And we're going to interpret this as the neural net's assignment for how likely every one of these characters, 27 characters.
Yeah, so what he's explaining here, right? So props 0. So you have this array, this tensor of 27 characters, and basically what this eventually outputs, what I mentioned, this is our output eventually, which means that this first index of the tensor, this is the dots, this is A, B, C, D, E, F, G, etc., all the way to Z. So now it would, for example, say that with the input being, the first character being a dot, that the probability of the next character being a dot is 3.5%.
Are to come next. And as we tune the weights W, we're going to be, of course, getting different probabilities out for any character that you input. And so now the question is just, can we optimize and find a good W such that the probabilities coming out are pretty good? And the way we measure pretty good is by the loss function. Okay, so I organized everything into a single summary so that hopefully it's a bit more clear. So it starts here. We have an input data set. We have some inputs to the neural net, and we have some labels.
Oh boy, where did he start? Okay, we have here XS, YS, and PyTorch. he... Okay, so you are able to do that. Okay, hold on. So I have my X encoding here. And basically what he mentions... So what he does here as well is, let's do what he does as well and copy over the generator seed. So that we are up to date with what he is doing, and then torch.randomInt for W. Apparently we are able to give it a generator. Generator equals G. Okay, that compiles. Amazing. Let's remove it for a second. Let's remove this one as well. Let's remove the shape for a second. And just double check if we indeed have everything the same as he has. So 27, 27, X encoding. F.1, X number of classes to float. Then, for now, let's remove this. So logit is xenx with the weights. Logit exponential, probabilities. Okay.
For the correct next character in a sequence. These are integers. Here I'm using...
Let's just do probs.shape. We should expect 527 here, yeah.
torch generators now so that you see the same numbers that I see. And I'm generating 27 neurons weights. And each neuron here receives 27 inputs.
Yep.
Then here we're going to plug in all the input examples x's into a neural net. So here, this is a forward pass. First, we have to encode all of the inputs into one-hot representations. So we have 27 classes, we pass in these integers, and xinc becomes a array that is 5 by 27. Zeros, except for a few ones. We then multiply this in the first layer of a neural net to get logits, exponentiate the logits to get fake counts, sort of, and normalize these counts to get probabilities. So these last two lines, by the way, here, are called the softmax, which I pulled up here. Softmax is a very often used layer in a neural net that takes these z's, which are logits, exponentiates them, and divides and normalizes. It's a way of taking outputs of a neural net layer, and these outputs can be positive or negative, and it outputs probability distributions. It outputs something that is always sums to 1 and are positive numbers, just like probabilities. So it's kind of like a normalization function, if you want to think of it that way. And you can put it on top of any other linear layer inside a neural net, and it basically makes a neural net output probabilities. That's very often used, and we used it as well here. So this is the forward pass, and that's how we made a neural net output probability. Now, you'll notice that all of this entire forward pass is made up of differentiable layers. Everything here we can backpropagate through, and we saw some of the backpropagation in micrograph.
Alright. Before we continue, I first have to pee again, because I just finished a liter of water and coffee, so be right back again. And we can continue.
This is just multiplication and addition. All that's happening here is just multiply and add, and we know how to backpropagate through them. Exponentiation, we know how to backpropagate through. And then here we are summing, and sum is easily backpropagatable as well, and division as well. So everything here is a differentiable operation, and we can backpropagate through. Now, we achieve these probabilities, which are 5 by 27. For every single example, we have a vector of probabilities that sum to 1. And then here I wrote a bunch of stuff to sort of like break.
So what is he doing now? So for that vector, it's printing it out. Calculate the probability assigned by the net to the character. Fair enough.
Down the examples. So we have 5 examples making up Emma, right? And there are 5 bigrams inside Emma.
So .e, em, mm, ma, and a dot.
Bigram example 1 is that E is the beginning character right after dot. And the indexes for these are 0 and 5. So then we feed in a 0, that's the input to the neural net. We get probabilities from the neural net that are 27 numbers. And then the label is 5 because E actually comes after dot. So that's the label. And then we use this label 5 to index into the probability distribution here. So this index 5 here is 0, 1, 2, 3, 4, 5. It's this number here, which is here. So that's basically the probability assigned by the neural net to the actual correct character. You see that the network currently thinks that this next character, that E following dot, is only 1% likely, which is of course not very good, right? Because this actually is a training example, and the network thinks that this is currently very, very unlikely. But that's just because we...
And if we compare that to like the matrix that we had here, so .e is like, it's very, very likely. So when we would backpropagate through this, like the loss function would be quite high.
In generating a good setting of W. So right now this network thinks this is unlikely, and 0.01 is not a good outcome. So the log likelihood then is very negative, and the negative log likelihood is very positive. And so 4 is a very high negative log likelihood, and that means we're going to have a high loss. Because what is the loss?
Exactly.
The loss is just the average negative log likelihood. So the second character is EM. And you see here that also the network thought that M following E is very unlikely, 1%. For M following M, it thought it was 2%. And for A following M, it actually thought it was 7% likely. So just by chance, this one actually has a pretty good probability and therefore a pretty low negative log likelihood. And finally here, it thought this was 1% likely. So overall, our average negative log likelihood, which is the loss, the total...
So again, what we will do eventually, like right now we are doing all things with XS, and we will do the backpropagation. We will compare it to YS, and YS is like the output of what we have here.
Loss that summarizes...
Now thinking of it, we might have to do some manipulation on YS also. That's why I had that hot encoding for YS as well, I think.
Basically, how well this network currently works, at least on this one word, not on the full data set, just the one word, is 3.76, which is actually fairly high loss. This is not a very good setting of W's.
No.
We're currently getting 3.76. We can actually come here and we can change our W. We can resample it. So let me just add 1 to have a different seed, and then we get a different W, and then we can rerun this. And with this different setting of W's, we now get 3.37. So this is a much better W, right? And it's better because the probabilities just happen to come out higher for the characters that actually are
Yeah.
indexed. And so you can imagine actually just resampling this. We can try 2.
Oh wait, he already compared the YS over here. I see. Yeah.
So, okay, this was not very good. Let's try one more. We can try 3. Okay, this was terrible setting because we have a very high loss. So anyway, I'm going to erase this. What I'm doing here, which is just guess and check of randomly assigning parameters and seeing if the network is good, that is amateur hour. That's not how you optimize it. The way you're optimizing it.
Yeah, that's indeed amateur hour. Like, imagine like that at Anthropic or OpenAI or at XAI that they're just like changing the weights manually every time, incrementing one whomp, and even with the newest model of of like Grok that has like I think it was 1 trillion parameters.
Is you start with some random guess, and we're going to commit to this one, even though it's not very good. But now the big deal is we have a loss function. So this loss is made up.
Yeah, so let me quickly just take over what he has been doing as well, just so that I do not get too far behind. I dot item. Am I going to print it like yes? I can't be bothered actually to do that, so let's just copy over the like the logic, which is the most important. Log b storage.log. Not capital P. Negative loss equals negative log b. And then negative loss I equals negative loss. I mean, in theory, what we could do, I know he does this for a reason, right? But what you could just do is that instead of caching it, just immediately put negative loss function there. I mean, that's a little bit easier. Main item, and we should get. I think he had 3.76 as well. I think.
Only of differentiable operations, and we can minimize the loss by tuning W's, by computing the gradients of the loss with respect to these W matrices.
By the way, the way that he goes over it, like with the steps, it's better to learn, but if you see that you don't have to cache it in separate variables, like with the naming, it's good, but right now this is also very, like, I don't need to like have the logarithmic loss in a separate cached variable and then turning that to a negative. You can just do it in once and then set it directly to the index.
And so
Just as easy. But for learning, he is right to like separate it out.
Minimize the loss and find a good setting of W using gradient-based optimization. So let's see how that will work. Now things are actually going to look almost identical to what we had with micrograd. So
that was micrograd, yeah.
here, I pulled up the lecture from micrograd, the notebook. It's from this repository. And when I scroll all the way to the end where we left off with micrograd, we had something very, very similar. We had a number of input examples. In this case, we had 4 input examples inside x's, and we had their targets, desired targets. Just like here, we have...
He's literally making a linear output. Like, he's not even putting one hidden layer in it. He's literally like, oh no, we're just input, output, done. I mean, that's indeed the most basic forms of neural networks. It doesn't even have like I'm not sure if you can even call it the network, but yeah, it's possible.
now, but with 5 of them, and they're now integers instead of vectors. But we're going to convert our integers to vectors, except our vectors will be 27 large instead of 3 large.
Yeah.
And then here what we did is first we did a forward pass where we ran a neural net on all of the inputs to get predictions. Our neural net at the time, this n of x, was a multi-layer perceptron. Our neural net is going to look different because our neural net is just a single layer, single linear layer followed by a softmax. So that's our neural net. And the loss here was the mean squared error. So we simply subtracted the prediction from the ground truth and squared it and summed it all up. And that was the loss. And loss was the single number that summarized the quality of the neural net. And when loss is low, like almost 0, that means the neural net is predicting correctly.
If this is finished, probably what I will do and try out myself is like change this into a multi-layer perceptron and then indeed see what happens with predicting of new names, etc. Just to like practice a little bit with it.
So we had a single number that that summarized the performance of the neural net, and everything here was differentiable and was stored in a massive compute graph. And then we iterated over all the parameters. We made sure that the gradients are set to 0, and we called loss.backward. And loss.backward initiated backpropagation at the final output node of loss, right? So yeah, remember these expressions? We had loss all the way at the end. We start backpropagation, and we went all the way back. And we made sure that we
that first video, for real, it was actually very fun to do it. Like, I think the video was like 2.5 hours. But going through it and like actually understanding of how a neural network works, like a graph, like forward passes and backpropagation, it's really interesting. And I think that if you want to go into data science and want to learn how to create these kinds of things, you at least have to understand the basics of it. Like, a lot of it is right now taken care of by, of course, like libraries like PyTorch, but it's still good to understand what's actually happening.
all the parameters .grad. So .grad started at 0, but backpropagation filled it in. And then in the update, we iterated all the parameters, and we simply did a parameter update where every single element of our parameters was nudged in the opposite direction of the gradient.
Yeah.
And so we're going to do the exact same thing here. So I'm going to pull this up on the side here so that we have it available. And we're actually going to do the exact same thing.
I wonder if he's actually going to use micrograd and not PyTorch. Yeah.
So this was the forward pass. So we did this.
So this was the forward pass. Let's remove that for a second. Am I going to do it that way? I will just follow him for a while.
So now we have to evaluate the loss, but we're not using the mean squared error. We're using the negative log likelihood because we are doing classification. We're not doing regression, as it's called. So here we want to calculate loss.
Yeah, so let's quickly just remove this and then follow what he's doing now.
Now, the way we calculate it is just this average negative log likelihood. Now, this probs here has a shape of 5 by 27. And so to get all the, we basically want to pluck out the probabilities at the correct indices here. So in particular, because the labels are stored here in the array y's, basically what we're after is, for the first example, we're looking at probability of 5, right, at index 5. For the second example, at the second row, or row index 1, we are interested in the probability assigned to index 13. At the second example, we also have 13. At the third row, we want 1.
Yeah, so he just wants to match it. So what we're going to do probably is like just a for loop, right? For each item, and then, yeah.
So these are the probabilities we're interested in, right? And you can see that they're not amazing, as we saw above. So these are the probabilities we want, but we want like a more efficient way to access these probabilities, not just listing them out in a tuple like this. So it turns out that the way to do this in PyTorch, one of the ways at least.
Okay, he's going for PyTorch. That's nice.
All of these. Sorry about that. All of these integers in vectors. So these ones, you see how they're just 0, 1, 2, 3, 4. We can actually create that using torch.arrange of 5. 0, 1, 2, 3.
Torch.arrange 5. Hey!
So we can index here with torch.arrange of 5, and here we index with y's.
Oh, that's actually these are things that I don't know about Python yet, like that you can do that kind of stuff. That's so nice. That's so nice. So we go into our props tensor, and then we do that automatically. That's so much easier than doing it in C#. My God.
And you see that that gives us exactly these numbers. So that plucks out the probabilities that the neural network assigns to the correct next character. Now we take those probabilities and we don't.
Okay, if I see things like this, I can imagine why people like Python. Like in C#, probably I would have to do it. You would have to do the matching yourself. Like, and Python apparently does it on the back end for you. Like, my God, I now understand why people like it for data science. It's so much easier. My God.
We actually look at the log probability. So we want to .log, and then we want to just average that out. So take the mean of all of that, and then it's the negative.
Yeah, because we want the negative log function and then the average. Yeah, makes sense.
Average log likelihood, that is the loss. So the loss here is 3.7 something, and you see that this loss, 3.76 is exactly as we've obtained before, but this is a vectorized form of that expression. So we get the same loss. And this same loss we can consider sort of as part of this forward pass, and we've achieved here now loss. Okay, so we made our way all the way to loss. We defined the forward pass. We forwarded the network and the loss. Now we're ready to do the backward pass. So backward pass. We want to first make sure that all the gradients are reset, so they're at 0. Now in PyTorch, you can set the gradients to
0 grad.
Also just set it to none, and setting it to none is more efficient. And PyTorch will interpret none as like the lack of a gradient, and it's the same as zeros. So this is a way.
Hold on, is it actually? But 0 grad actually sets to 0 as well. I wonder what the reason behind that is. Why none is quicker.
To set to 0 the gradient. And now we do loss.backward. Before we do loss.backward, we need one more thing. If you remember from micrograd, PyTorch actually requires that we pass in requires grad is true.
Yeah. And this was the issue that I had previously. I'm not sure if it will pick this up. It does! Okay.
So that
So when I was doing micrograd, when I had to do like the requires a grad part, like for every individual neuron, it was giving me issues.
We tell PyTorch that we are interested in calculating the gradient for this leaf tensor. By default, this is false. So let me recalculate with that. And then set to none and loss.backward. Now, something magical happened when loss.backward was run. Because PyTorch, just like micrograd, when we did the forward pass here, it keeps track of all the operations under the hood. It builds a full computational graph. Just like the graphs we produced in micrograd, those graphs exist inside PyTorch. And so it knows all the dependencies and all the mathematical operations of everything. And when you then calculate the loss, we can call a dot backward on it. And dot backward then fills in the gradients of all the intermediates all the way back to W's, which are the parameters of our neural net. So now we can do W.grad, and we see that it has structure. There's stuff inside it. And these gradients, every single element here, so W.shape is 27 by 27, W.grad's shape is the same, 27 by 27. And every element of W.grad is telling us the influence of that weight on the loss function. So for example, this number all the way here, if this element, the 0, 0 element of W, because the gradient is positive, it's telling us that this
And remember, 0, 0 is like dot dot.
Influencing the loss. Slightly nudging W, slightly taking W 0, 0 and adding a small h to it would increase the loss mildly because this gradient is positive. Some of these gradients are also negative. So that's telling us about the gradient information, and we can use this gradient information to update the weights of this neural network. So let's now do the update. It's going to be very similar to what we had in micrograd. We need no loop over all the parameters because we only have one parameter, tensor, and then W. So we simply do W.data plus equals we can actually copy this almost exactly.
Wait.
-1 times W.
He's going to do it that way. Is that actually... We don't have to walk over it. Okay, that's interesting.
W.grad. And that would be the update to the tensor. So that updates.
Oh, of course, because we do it times the grad of it. Yeah, that makes sense. That makes sense. Okay, yeah.
The tensor. And because the tensor is updated, we would expect that now the loss should decrease. So here, if I print loss that item, it was 3.76, right? So we've updated the W here. So if I recalculate forward pass, loss now should be slightly lower. So 3.76 goes to 3.74. And then we can again set grad to none and backward, update, and now the parameters changed again. So if we recalculate the forward pass, we expect a lower loss again, 3.72. Okay, and this is again we're now doing gradient descent. And when we achieve a low loss,
That's so interesting.
that will mean that the network is assigning high probabilities to the correct next characters. Okay, so I rearranged everything and I put it all together.
He has put it all together, he says. Oh. So interesting that he puts the this part here, right? Let's add all those things here. Then let's see if that's correct. I think it's correct. Should be correct, right? X encoding, F1 number of classes, float, logic exponential, counts, true. Prob storage range, num. Is it correct? I think it is actually correct, but where? Oh, he goes about it that way. That is actually very smart of him. Because we're not only working with Emma, we're now also working with different things. So just to double check, was everything there seems to be alright. Let's also do the exact same thing as him so that we get, just to double check, num. Then we have the manual seed generator, 2727, G regards true for E range 10. Nice, works.
From scratch. So here is where we construct our data set in bigrams. You see that we are still iterating only over the first word, Emma. I'm going to change that in a second. I added a number that counts the number of elements in Axis so that we explicitly see that the number of examples is 5. Because currently we're just working with Emma. And there's 5 bigrams there. And here I added a loop of exactly what we had before. So we had 10 iterations of gradient descent of forward pass, backward pass, and an update. And so running these two cells, initialization and gradient descent, gives us some...
I'm going to take a few quicker steps because... Ta-da! We are getting quicker to 0. Normally you would not do this, obviously, and very easy how I could fix this would be like that. Like just adding a lot of things to it. Alright.
On the last mission. But now I want to use all the words. And there's not 5, but 228,000 bigrams now. However, this should require no modification whatsoever. Everything should just run, because all the code we wrote doesn't care if there's 5 bigrams or 228,000 bigrams.
Yeah.
And with everything it should just work.
And that works due to the fact that he now uses number.xs instead of 5 hard-coded.
You see that this will just run. But now we are optimizing over the entire training set of all the bigrams. And you see now that we are decreasing very slightly. So actually we can probably afford those.
Hold on. Remove! Really? Hey!
Larger learning rate.
Noise.
You can probably afford even larger learning rate.
So if we want to very quickly speed this up, normally you wouldn't do this. And the closer you get to your target, like what you normally would do is like that you slow down the step sizing. Like this, normally you wouldn't take these kinds of large step sizes. It's insane. It's so fun to see something like this working. I love it.
Even 50 seems to work on this very, very simple example, right? So let me reinitialize. And let's run 100 iterations. See what happens. Okay. We seem to be coming up to some pretty good losses here. 2.47. Let me run 100 more. What is the number that we expect, by the way, in the loss? We expect to get something around what we had originally, actually. So all the way back, if you remember, in the beginning of this video,
which was 2.3 something, right?
Just by counting, our loss was
2.4.
2.47 after we added smoothing.
2.47.
But before smoothing, we had roughly 2.45 likely.
Yeah.
Loss. And so that's actually roughly the vicinity of what we expect to achieve. But before we achieved it by counting, and here we are achieving roughly the same result, but with gradient-based optimization. So we come to about 2.46, 2.45, etc. And that makes sense because fundamentally we're not taking any additional information. We're still just taking in the previous vector and trying to predict the next one. But instead of doing it explicitly by counting and normalizing, we are doing it with gradient-based learning. And it just so happens that the explicit approach happens to very well optimize the loss function without any need for gradient-based optimization, because the setup for Bigram language models is so straightforward, it's so simple. We can just afford to estimate these probabilities directly and maintain them in a table. But the gradient-based approach is significantly more flexible. So we've actually gained a lot, because what we can do now is we can expand this approach and complexify the neural net. So currently we're just taking a single character and feeding into a neural net, and the neural net is extremely simple. But we're about to iterate on this substantially. We're going to be taking multiple previous characters, and we're going to be feeding them into increasingly more complex neural nets. But fundamentally, the output of the neural net will always just be logits. And those logits will go through the exact same transformation. We are going to take them through a softmax, calculate the loss function and the negative log likelihood, and do gradient-based optimization. And so actually, as we complexify the neural nets and work all the way up to transformers, none of this will really fundamentally change. None of this will fundamentally change. The only thing that will change is the way we do the forward pass, where we've taken some previous characters and calculated logits for the next character in the sequence. That will become more complex, and we'll use the same machinery to optimize it.
So that means basically that like your input will change a little bit, right? So right now what goes in is XS, and XS is YX1, which is one character. So basically what will change, this tensor will change in dimension. That's what I would think that he is talking about.
And it's not obvious how we would have extended this Bigram approach into a case where there are many more characters at the input, because eventually these tables would get way too large because there's way too many combinations of what previous characters
Yeah.
could be. If you only have one previous character, we can just keep everything in a table that counts. But if you have the last 10 characters that are input, we can't actually keep everything in the table anymore. So this is fundamentally an unscalable approach, and the neural network approach is significantly more scalable, and it's something that actually we can improve on over time. So that's where we will be digging next. I wanted to point out two more things. Number one, I want you to notice that this xenc here, this is made up of one-hot vectors. And then those one-hot vectors are multiplied by this W matrix. And we think of this as multiple neurons being forwarded in a fully connected manner. But actually what's happening here is that, for example, if you have a one-hot vector here that has a 1 at, say, the 5th dimension, then because of the way the matrix multiplication works, multiplying that one-hot vector with W actually ends up plucking out the 5th row of W. Logits would become just the 5th row of W. And that's because of the way the matrix multiplication works. So that's actually what ends up happening.
Why he's doing this, by the way, has to do indeed with how matrix multiplication works. So if you're multiplying, it's like you're cross multiplying basically with matrix multiplications. So let me see if I can actually get an example of this. So this is basically how matrix multiplication works, right? So when he is talking about doing this, all that he is saying is that he is, so we have the row and then we make the dot product of multiplying this by this, and then you get that, which is basically 1 times 7 times 2 times 3. So that is 21. Anyway, that's how you go about it. It's quite fun actually how it works. Let's see if this one is a little bit better in it. Yeah, this one explains it very nicely. Oh well. Let's continue.
That's actually exactly what happened before. Because remember, all the way up here, we have a bigram. We took the first character, and then that first character indexed into a row of this array here. And that row gave us the probability distribution for the next character. So the first character was used as a lookup into a matrix here to get the probability distribution. Well, that's actually exactly what's happening here. Because we're taking the index, we're encoding it as 1 hot and multiplying it by W. So logits literally becomes the
Just to ensure, like I mentioned that I might want to try this and like change it into a multi-layer perceptron. I'm not sure what part 2 will be, because he is going to like extend it with sequences yet, like dimensions of the input tensor. That's what I think. So I will wait a second before doing that.
the appropriate row of W. And that gets, just as before, exponentiated to create the counts, and then normalized and becomes probability. So this W here is literally the same as this array here. But W, remember, is the log counts, not the counts. So it's more precise to say that W exponentiated, W.x, is this array. But this array was filled in by counting and by basically populating the counts of bigrams, whereas in the gradient-based framework, we initialize it randomly, and then we let the laws guide us to arrive at the exact same array. So this array exactly here is basically the array W
And
at the end of optimization.
what he mentions here is very you have to listen to it very carefully. Like after training and optimization. So this array that we created with gradient descent in this model, it's not really a model. Like it's a single layer, but what we knew, right, was that the loss function of this over here apparently was 2.4544. We only have the same array if our loss function here will be the same. Then we will literally have the same counts or n counts, what he's explaining, like this matrix.
Except we arrived at it piece by piece by following the laws. And that's why we also obtain the same loss function at the end. And the second note is, if I come here, remember the smoothing where we added fake counts to our counts in order to smooth out and make more uniform the distributions of these probabilities. And that prevented us from assigning 0 probability to any one bigram. Now, if I increase the count here, what's happening to the probability? As I increase the count, probability becomes more and more uniform, right? Because these counts go only up to like 900 or whatever. So if I'm adding plus a million to every single number here, you can see how the row and its probability then when we divide is just going to become more and more close to exactly even probability, uniform distribution.
Yeah.
turns out that the gradient-based framework has an equivalent to smoothing. In particular, think through these W's here, which we initialize randomly. We could also think about initializing W's to be 0. If all the entries of W are 0, then you'll see that logits will become all 0, and then exponentiating those logits becomes all 1, and then the probabilities turn out to be exactly uniform. So basically, when W's are all equal to each other, or say especially 0, then the probabilities come out completely uniform. So trying to incentivize W to be near 0 is basically equivalent to label smoothing. And the more you incentivize that in the loss function, the more smooth distribution you're going to achieve. So this brings us to something that's called regularization, where we can actually augment the loss function to have a small component that we call a regularization loss. In particular, what we're going to do is we can take W, and we can, for example, square all of its entries, and then we can, sorry about that. We can take all the entries of W and we can sum them. And because we're squaring, there will be no signs anymore. Negatives and positives all get squashed to be positive numbers. And then the way this works is you achieve 0 loss if W is exactly or 0. But if W has non-zero numbers, you accumulate loss. And so we can actually take this and we can add it on here. So we can do something like loss plus W squared dot sum. Or let's actually, instead of sum, let's take a mean, because otherwise the sum...
Interesting that it goes that way. So you would adapt your loss function a little bit more this way.
Gets too large. So mean is like a little bit more manageable. And then we have a regularization loss here, like say 0.01 times, or something like that.
That is
You can
interesting.
choose the regularization strength. And then we can just optimize this. And now this optimization actually has two components. Not only is it trying to make all the probabilities work out, but in addition to that, there's an additional component that simultaneously tries to make all W's be 0. Because if W's are not 0, you feel a loss. And so minimizing this, the only way to achieve that is for W to be 0. And so you can think of this as adding like a spring force or like a gravity force that pushes W to be 0. So W wants to be 0 and the probabilities want to be uniform, but they also simultaneously want to match up your probabilities as indicated by the data. And so the strength of this regularization is exactly controlling the amount of counts that you add here. Adding a lot more counts here corresponds to increasing this number. Because the more you increase it, the more this part of the loss function dominates this part, and the more these weights will be unable to grow, because as they grow, they accumulate way too much loss.
That's actually what we see here as well. Like the way it's training right now, it's way slower than once you did how you did it before, right?
And so if this is strong enough, then we are not able to overcome the force of this loss, and we will never, and basically everything will be uniform predictions. So I thought that's kind of cool. Okay, and lastly, before we wrap up, I wanted to show you how you would sample from this neural net model. And I copy-pasted the sampling code from before, where remember that...
Let's quickly grab our sampling code as well. Which was this, if I am correct? Yes, it was this. So we have our out, while true, bx, ix, torch, yeah, okay.
We sampled 5 times, and all we did is we start at 0, we grabbed the current ix row of p, and that was our probability row, from which we sampled the next index and just accumulated that and break when 0. And running this gave us these results. I still have the p in memory, so this is fine. Now the speed doesn't come from the row of B. Instead, it comes from this neural net. First, we take.
Why is doing neural net? Because it's not really a neural net. It's like input and a linear output, which with trained weights.
Yes. And we encode it into a one-hot row of xenc. This xenc multiplies RW, which really just plucks out the row of W corresponding.
Okay, so hold on, how he's doing this. Ix is 0. Torch something. Let's just quickly follow this xn code. F.OneShot. Torch.tensor. Before I continue here in a second, I want to read actually what's happening here. So we are encoding our IX. Which is 0. So it's the start. So we start, we have something. Then we multiply it by our weights. Exponential. Keep dimension. Multinomial. That is actually interesting. Name true is not defined. What? It's not. It's true. And we get the same result. That's interesting.
And that gets our logits, and then we normalize those logits, exponentiate to get counts, and then normalize to get the distribution, and then we can sample from this distribution. So
this was literally the same result, I think, that we got. Yeah, here. That's so cool.
Kind of anticlimactic or climatic, depending how you look at it, but we get the exact same result.
Yeah.
And that's because this is in the identical model. Not only does it achieve the same loss, but as I mentioned, these are identical models, and this W is the log counts of what we've estimated before. But we came to this answer in a very different way, and it's got a very different interpretation. But fundamentally, this is basically the same model and gives the same samples here. And so
that's so interesting. Yeah.
Okay, so we've actually covered a lot of ground.
Okay, hold on. Let's see.
And so that's kind of cool.
Okay, look at his smirk. Like, that's kind of cool. It's the same as mine. Like, it's like, yeah, that's kind of cool. Yeah, it is. It is kind of cool.
Okay, so we've actually covered a lot of ground. We introduced the Bigram character level language model. We saw how we can train the model, how we can
It is kind of cool.
how we can evaluate the quality of the model using the negative log likelihood loss. And then we actually trained the model in two completely different ways that actually give the same result from the same model. In the first way, we just counted up the frequency of all the bigrams and normalized. In the second way, we used the negative log likelihood loss as a guide to optimizing the counts matrix or the counts array so that the loss is minimized in a gradient-based frame. and we saw that both of them give the same result, and that's it. Now the second one of these, the gradient-based framework, is much more flexible. And right now, our neural network is super simple. We're taking a single previous character, and we're taking it through a single linear layer to calculate the logits. This is about to complexify. So in the follow-up videos, we're going to be taking more and more of these characters, and we're going to be feeding them into a neural net. But this neural net will still output the exact same thing. The neural net will output logits. And
Yeah, again, so what I think that he's going to do is that we are going to add multiple dimensions potentially um, into the neural net. But I might be wrong there. I might be wrong.
these logits will still be normalized in the exact same way, and all the loss and everything else in the gradient-based framework, everything stays identical. It's just that this neural net will now complexify all the way to transformers. So
It's actually quite interesting because this is the first step towards like creating a tokenizer. Eventually, what tokens are is basically just one step further than what we are doing right now. A tokenizer is literally just right now we're doing character by character and we're working towards like eventually getting more characters. The tokenizer basically what it does is it's like it grabs a section and then it does the same thing like we're doing right here. So and I think that that's the cool part about what Andre is doing here. Like that you start with learning okay how do neural networks work and then you're eventually building towards like making GPT-2 in theory.
that's going to be pretty awesome, and I'm looking forward to it. For now, bye.
Yeah, Andre, for real, amazing video, and I will probably do this next part two of makemore tomorrow or something like that. So everyone, if you are here, thank you for watching. Thank you for the questions, Stefan and Ara. Maybe I will talk to you guys later. And yeah, thank you for your time. I hope you enjoyed it. If you would like me to explain certain things a little bit more along the line while I'm learning as well, or have any questions about what I do, who I am, feel free to ask them always during the live chats, and I'm happy to answer that. So bye bye and enjoy your day.